At the heart of our galaxy, in a region cloaked by thick clouds of interstellar dust and seething magnetic fields, lies one of the most powerful and unforgiving forces in the universe, a supermassive black hole named Sagittarius A. For millions of years, it has sat in silent dominance, an invisible predator warping time and space, consuming anything that dares to cross its gravitational threshold. It is a cosmic behemoth over 4 million times the mass of our Sun, and until recently, everything that drifted too close to it met an inevitable and violent end. But in the early 2010s, astronomers witnessed something extraordinary. A delicate cloud of gas, known simply as G2, was spotted on a direct collision course with Sagittarius A. Floating through space like a ghost, this dusty cloud, just a few times more massive than Earth, seemed destined for destruction. Predictions flooded the astrophysical community. As G2 approached the black hole, it would be torn apart by overwhelming tidal forces, its gas stripped and swallowed, triggering a brilliant flare as it fed the monstrous appetite of the galactic core. Telescopes around the world were trained on the scene, eager to witness the cosmic spectacle, an event unlike any other, unfolding 26,000 light-years from Earth. The countdown to doom had begun. But then, something completely unexpected happened. Nothing. G2 approached the event horizon. It brushed past the mouth of the gravitational abyss. And it lived. No brilliant flare. No dramatic explosion. No feeding frenzy. The gas cloud, stretched, but intact, passed by the black hole and continued on its journey, leaving scientists stunned. It was a moment that rewrote expectations. How could something so fragile survive a close encounter with the most destructive force in the galaxy? Was G2 more than just a gas cloud? Did it possess some hidden core? Or was our understanding of black holes fundamentally flawed? This wasn't just a survival story. It was a cosmic mystery, a paradox drifting through the most dangerous region in the Milky Way. G2's resilience forced astronomers to reconsider their models of accretion, tidal forces, and black hole behavior. It ignited debates, fueled new simulations, and prompted the search for other enigmatic objects near the galactic center. In this deep dive, we will journey through the full saga of G2. From its discovery in 2011 to its unlikely survival in 2014, and into the continuing debates and implications that ripple through astrophysics today. We will explore the true nature of this mysterious object, the monster it dared to approach, and the broader questions it raised about the nature of matter, gravity, and galactic evolution. In a universe governed by destruction and collapse, G2 was a whisper of resistance. A ghost that danced with a monster, and lived to tell the tale. But before we continue, subscribe to the channel and like the video. The story of G2 truly began in 2011, buried deep within the luminous chaos of the Milky Way's core. It was in that year that a team of astronomers, while studying the region surrounding Sagittarius A, detected a strange, compact object moving rapidly toward the galactic center. The discovery didn't come from a sudden burst of light or dramatic motion, but from the quiet, patient gaze of infrared telescopes trained on the heart of the galaxy. In visible light, the region around Sagittarius A is nearly impenetrable, blocked by thick clouds of dust and gas that have hidden the galactic center from view for centuries. But in the infrared spectrum, the cosmos opens up like a curtain parting on a stage. Using the Very Large Telescope, VLT, in Chile, equipped with the Symphony instrument, an adaptive optics system that allowed researchers to pierce through the haze with precision, scientists began to notice subtle but intriguing changes in the fabric of that dense environment. There, in the crowded stellar jungle near the black hole, they saw it, a faint, glowing blob of ionized hydrogen gas emitting bracket gamma emission lines, which are specific markers of warm, excited hydrogen. It was small, barely registering as significant at first glance, but it had one unmistakable trait: it was moving. And not just moving randomly, but accelerating, arcing inward on a highly elliptical trajectory, straight toward the center of the galaxy. It was this path that drew attention. By tracking its velocity and comparing observations over time, scientists realized they were watching something extraordinary unfold: a compact, luminous object seemingly destined to have a close encounter with the very heart of darkness. At first, there was a wave of cautious excitement. The object, quickly designated G2, did not behave like a star. Its spectral properties were diffuse, like a cloud. It had no firm point source signature. It emitted infrared light like heated dust and gas, not like the clean, sharp emission of a stellar body. It appeared to lack the internal structure necessary to survive what lay ahead. In a region known for devouring everything that strays too close, this object was thought to be doomed from the beginning. Over the next several months, more instruments joined the investigation. The Keck Observatory in Hawaii began taking measurements, supplementing the data from the VLT. Infrared imaging and spectroscopy were key. Only through these wavelengths could astronomers keep visual contact with G2 as it threaded its way through the cosmic fog. By late 2011, the motion of G2 was clear. It was headed straight toward Sagittarius A, on a trajectory that would take it dangerously close to the event horizon by 2014. What was most surprising wasn't just the path G2 was on, it was the timing. The encounter would happen in just a few years, well within the lifespan of current instruments, making it a rare chance to watch something fall into a black hole in real time. Such an opportunity was practically unprecedented. Astronomers had long theorized about what would happen if a gas cloud got too close to a black hole, but the chance to see it, to observe the physics of destruction as they happened, that was something else entirely. There was a buzz across the astrophysical community. Theorists began modeling the likely outcomes. Would G2 be shredded into filaments by tidal forces? Would its gas light up as it spiraled in, forming a mini accretion disk? Would Sagittarius A awaken from its relative quiet with a powerful flare? The models painted a vivid picture of fireworks to come. But there was also mystery in the object itself. Even in these early days, there were questions about its true nature. Some measurements showed that G2 was elongating as it moved, which made sense for a gas cloud under tidal stress. But others hinted at a more complex internal structure. Its brightness fluctuated. Its motion was slightly odd. Some proposed it might be more than just a cloud. But at this stage, those were just whispers, possibilities clouded by distance and uncertainty. For now, the facts were clear. In 2011, humanity found itself with a front-row seat to a rare cosmic drama. A fragile object had been discovered, hurtling through the densest, most violent region of our galaxy, on a path that would take it terrifyingly close to the most powerful gravitational force in the Milky Way. The clock had started ticking. At first glance, G2 appeared to be exactly what its spectral signature suggested, a relatively small cloud of ionized gas and dust, floating through the galactic center like a mist adrift in a hurricane. It was faint, diffuse, and seemingly simple, a blob of warm hydrogen gas glowing in the infrared, with no obvious core or structure. Based on early measurements, astronomers estimated its mass to be roughly 3 times that of Earth, not a significant amount by galactic standards, especially in the vicinity of a supermassive black hole. But despite its modest size, G2's presence stirred the curiosity of astronomers everywhere. Composed primarily of hydrogen, G2 emitted strong bracket gamma lines in the infrared spectrum, indicating that it was both ionized and relatively hot, likely heated by the intense radiation and energetic environment near the galactic center. Dust grains mixed within the cloud also radiated in the infrared, allowing scientists to observe and track its motion even through the thick fog of the Milky Way's core. The fact that it was detectable at all was a testament to the technological power of instruments like the VLT and Keck's near-infrared spectrometers, which could resolve such a faint, transient object amid the brilliance and confusion of nearby stars and gas. It was not spherical. It had no clear boundary. It moved like a wisp of vapor in slow collapse. But even this cloud, drifting like a thread in the wind, held more complexity than initially assumed. In basic terms, G2 was described as a dusty, ionized gas cloud, an interstellar object not unlike the many clumps and blobs seen in other parts of the galaxy, especially in regions of star formation or near supernova remnants. Yet its proximity to Sagittarius A made it inherently different. Here, in one of the most extreme gravitational environments known, every molecule of hydrogen was under stress. Tidal forces were already acting on it, even from a distance of hundreds of astronomical units. The cloud was not moving through calm space, it was on a descent into chaos. What made G2 especially unusual was its persistence. Unlike other short-lived clumps of gas that dissipate quickly, G2 seemed cohesive. It maintained its structure over time as it fell inward. It moved in a coherent, trackable arc, not scattered or fragmented as a truly loose cloud might be expected to behave. Observations showed that as it approached Pericenter, the point of closest approach to the black hole, G2 began to stretch along its trajectory, but it did not dissolve or vanish. This odd tenacity made astronomers start to wonder whether G2 was truly just a gas cloud. After all, typical gas clouds near the galactic center are prone to disruption. Random motions, interactions with stellar winds, radiation pressure, and gravitational shearing all tend to fragment such objects quickly. And yet, G2 held together. Its trajectory was remarkably clean. Its core remained visible. For a clump of gas just a few Earth masses in size, this was peculiar. The idea that G2 might be more than it seemed, a kind of cosmic Trojan horse, would emerge later. But at this stage, G2 was classified as a gas cloud. It had no visible star within it. It emitted no light of its own outside of its dust and gas emissions. There was no evidence of fusion or stellar activity. It was not orbiting anything small, it was on a plunge towards something massive. And it was fast. G2's velocity, as it spiraled towards Sagittarius A, increased dramatically. Its acceleration revealed the grip of gravity tightening with every passing month. Calculations showed it would reach speeds of thousands of kilometers per second at Pericenter, an unimaginable speed for such a fragile object. And still, it kept its form. So, while G2's early description seemed simple, just a dusty, ionized cloud, it was already proving to be anything but ordinary. Its mass may have been low, its size may have been small, but its story was just beginning. Because in the violent, unpredictable core of our galaxy, even a faint cloud of gas can challenge the laws of astrophysics. To understand the strange and dramatic journey of the G2 cloud, one must appreciate the brutal environment it was drifting through. G2 wasn't just floating somewhere in the distant cosmos, it was threading a needle through the most volatile, gravitationally complex neighborhood in the entire Milky Way. Its position, trajectory, and proximity to Sagittarius A made it not only a unique scientific curiosity, but also an unintentional test subject of nature's most extreme conditions. This wasn't a leisurely path through the galactic suburbs. This was a gas cloud hurling itself into the very furnace of creation and destruction, a place astronomers call the galactic center. Roughly 26,000 light-years away from Earth, the core of the Milky Way is a region packed with mystery and violence. Though we can't see it in visible light due to the thick lanes of interstellar dust that wind through our galaxy, infrared and radio observations reveal a chaotic realm dominated by Sagittarius A, the supermassive black hole anchoring our spiral home. This region is brimming with stars, some ancient, others born in violent clusters. It's packed with interstellar gas clouds, magnetic fields, relativistic particles, and tidal shearing forces that bend matter and time in ways that defy ordinary understanding. Amidst this mayhem, G2's position wasn't just close to the action, it was part of it. Early tracking data showed that G2 was not simply orbiting the black hole at a safe distance. It was falling toward it on a plunging, elliptical orbit set to bring it within a few hundred astronomical units of the black hole's event horizon. For context, 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. And G2's closest approach, or Pericenter, would take it within $260 of Sagittarius A. That may seem like a wide berth, but in galactic terms, it's uncomfortably close. This is the domain where light curves, matter shreds, and time slows. This is where everything changes. To be positioned here, inside the innermost few light days of the galaxy, is like sitting on the rim of a cosmic volcano. The gravitational gradient in this area is steep and unforgiving. Even the light from stars passing nearby is warped by the immense gravitational pull of the black hole. This isn't empty space, it's a turbulent gravitational well, A crucible of forces that don't just destroy but can sometimes birth new structures, new patterns, and perhaps, new ways of thinking about how the universe works. The region is also exceptionally crowded. Within a few light-years of Sagittarius A, there are thousands of stars packed into a relatively small volume of space, many orbiting the black hole at incredible speeds, forming what's known as the nuclear star cluster. Among them are the famous S stars, like S2, which has been tracked for decades and helped prove the existence of the black hole by mapping its precise orbital path around it. These stars whip around the black hole on tight, fast orbits, some coming within mere light days of the event horizon. It's in this densely packed gravitational jungle that G2 found itself, dwarfed in mass but racing through the same cosmic maze. But G2's trajectory set it apart. While the S stars generally follow elliptical orbits that repeat in cycles, G2's path looked more like a one-time plunge. It was coming in fast, on a nearly radial orbit, like a dart thrown straight at the bullseye. Based on infrared tracking, astronomers mapped its velocity and position over time, and as the cloud accelerated, its projected path grew more and more ominous. It was headed for a direct encounter, and the sheer proximity of that encounter caught everyone's attention. What made this location even more intriguing was the role it played in helping astronomers study the black hole itself. Because Sagittarius A is relatively quiet compared to other known supermassive black holes, meaning it's not constantly feeding or flaring, events like this are rare opportunities. A gas cloud falling toward a black hole could serve as a natural experiment, offering a glimpse into how these monsters behave when something strays too close. It could shed light on accretion mechanics, flare production, energy release, and more. G2 was not just near Sagittarius A, it was a probe, of sorts, launched by nature itself into the jaws of a supermassive mystery. And the fact that G2 was only 26,000 light-years away made it even more significant. That's close in cosmic terms, well within our own galaxy. For reference, the Milky Way is about 100,000 light-years across, so G2 was practically in our astronomical backyard. That allowed for high-resolution observations using Earth-based telescopes. Unlike events that happen in distant galaxies, where data is fuzzy or faint, G2 offered an unprecedented chance to study black hole interactions in exquisite detail. Its proximity allowed researchers to collect rich datasets in real time, to watch as gravity and gas collided in one of the universe's most dynamic laboratories. The importance of location, in this case, can't be overstated. G2 was not just near a black hole, it was approaching the Milky Way's gravitational nucleus. It was embedded in the deepest part of the galaxy's gravitational potential well, where stars move like comets and light bends into rings. It was in a place where a single miscalculation could mean complete obliteration. Yet it wasn't vaporized in an instant, as expected. It was tracked, it was watched, and eventually it was seen to survive. Even more fascinating was the trajectory it followed. Not a leisurely orbit or a grazing pass, but a death dive. A deep plunge into the gravitational tide, skimming the edge of no return. Its orbit took it on a journey through curved space and accelerating frames of reference, forcing it to obey the warping of spacetime described by Einstein's general relativity. It wasn't just a location, it was a path, a story, a drama unfolding second by second as G2 raced toward the black hole with nothing to protect it but its own mystery. And still, it held together. Observations showed that even as it neared the point of no return, the cloud was not fragmenting in the way simulations had predicted. Yes, it was elongating. Yes, it was under immense stress. But it remained visible, coherent, a single object on a singular journey. As it moved through this violently gravitational landscape, it revealed secrets not just about itself, but about the environment it traveled through. G2's position, then, wasn't just geographical, it was symbolic. It stood at the boundary between the known and the unknown, the place where classical physics bends and relativistic chaos begins. In this liminal zone, G2 danced with a black hole and didn't disappear. That location, so perilous, so unique, is what made this story not only possible, but unforgettable. To truly understand the magnitude of what G2 was up against, we have to turn our attention to its cosmic adversary, Sagittarius A. The name may be deceptively simple, but what it refers to is anything but. Sagittarius A is not just a gravitational object, it's the dark beating heart of the Milky Way, a supermassive black hole whose scale and power defy ordinary comprehension. Situated at the precise center of our galaxy, Sagittarius A is the anchor around which everything else in the Milky Way revolves. Stars, gas clouds, cosmic dust, and dark matter, they all orbit this hidden monster, bound by its immense gravitational grip. First identified in the 1970s through intense radio emissions, Sagittarius A was initially a puzzle. Astronomers noted an unusually compact and bright source of radio waves emanating from the direction of the constellation Sagittarius. Over time, more data poured in, and the picture grew clearer. Something enormous was lurking at the center of the galaxy, something massive, compact, and invisible. It wasn't until the late 1990s and early 2000s, with the advent of adaptive optics and long-term monitoring of nearby stars, that the truth became undeniable. By tracking the orbits of individual stars, especially one in particular named S2, scientists could calculate, with high precision, the mass of the invisible object they were circling. The result was staggering. Sagittarius A weighs in at over 4 million times the mass of the Sun. And yet, all that mass is confined to a region smaller than our solar system. That kind of density cannot be anything but a black hole, a point of infinite gravity where not even light can escape. And not just any black hole, a supermassive one. The type found at the centers of galaxies. The type that shapes star formation, sculpts galactic evolution, and governs the fates of millions of solar systems around it. Unlike the bright, ravenous black holes observed in distant galaxies, ones that devour matter in brilliant displays of X-rays and relativistic jets, Sagittarius A is mostly quiet. It doesn't feed regularly. It doesn't flare often. In fact, it's considered to be in a relatively dormant phase, accreting material at a very slow rate. But that calmness is deceptive. It's not because the black hole is weak, it's because the environment around it is sparse, or because material hasn't crossed its threshold recently. When gas or stars do fall in, Sagittarius A can awaken with stunning displays of energy, temporarily blazing in the X-ray and infrared as it digests the infalling matter. Its event horizon, the boundary beyond which nothing can return, is estimated to be around 12 million kilometers in diameter. That's about 17 times the diameter of the Sun, yet the black hole's immense mass means it warps spacetime around it far more dramatically than its size suggests. The closer you get to Sagittarius A, the more physics begins to twist. Time slows. Light bends. Tidal forces become intense. And gravity takes on a whole new character, no longer a gentle pull, but a violent stretching and compression of everything in its path. The presence of Sagittarius A dominates its local environment in every possible way. Stars within a few light-years are compelled to follow hyperelliptical orbits, sometimes reaching thousands of kilometers per second. Gas clouds are torn into streams. Magnetic fields are twisted and contorted. This is not just a gravitational object, it's the central authority of the galaxy. Without it, the Milky Way's spiral structure would be chaotic. The very architecture of our home in the cosmos depends on the silent weight of this invisible entity. And yet, despite its dominance, Sagittarius A remains largely hidden from view. The black hole emits no light of its own. Everything we know about it comes from the things around it, the stars it influences, the radiation from matter swirling near the event horizon, and the gravitational waves it may someday release. In recent years, radio telescopes around the world have worked together to produce the first images of its silhouette, an effort culminating in 2022 with the Event Horizon Telescope's historic photo showing the shadow of Sagittarius A, a ring of fire surrounding a dark heart. A visual proof of what had been inferred for decades. This was the monster that G2 was destined to meet. Not a symbolic monster, not a mythic one, but a real, physical singularity. A hole in space-time itself. It had consumed stars in the past. It had shaped the dynamics of an entire galactic nucleus. It represented the end point of mass and light, the ultimate expression of collapse. G2 was no match. The odds were impossibly lopsided. A small cloud of gas, just 3 times the mass of Earth, drifting toward an object with 4 million solar masses compressed into a space no larger than Mercury's orbit. From the moment G2 was spotted, the outcome seemed inevitable. The gravitational forces alone should have been enough to tear it into filaments, to drag those filaments inward, to feed the black hole and trigger a flare visible across the galaxy. It was the perfect setup for a cosmic spectacle. One momentary flicker, one dramatic feast in the otherwise quiet life of Sagittarius A. But Sagittarius A, like so much in the universe, did not behave as expected. And that, more than the black hole's mass, more than its orbiting stars, more than its history, would become the true revelation of G2's story. Because in approaching the heart of the galaxy, G2 did not just dance with the monster. It forced the monster to reveal a little more of its true nature. From the moment G2 was first tracked in 2011, the astronomical community was electrified not only by what it was, but by where it was headed, and how soon it would arrive. Observations made it clear that this faint, dusty cloud of ionized gas was on a steep, highly eccentric orbit, one that would plunge it deep into the gravitational well of Sagittarius A by mid-2014. That meant there were only a few short years to prepare, observe, and anticipate what seemed like an inevitable cataclysm. For those studying black holes and accretion physics, this was a once-in-a-career opportunity to witness, in real time, an object fall into a supermassive black hole. Theoretical models quickly emerged to predict what would happen when G2 made its closest approach. Almost all of them pointed toward destruction. The reasoning was based on well-understood gravitational dynamics, particularly the immense tidal forces that black holes exert on nearby matter. These forces stretch and compress objects that approach the event horizon, a process often referred to as spaghettification. The closer something gets to the black hole, the more extreme the difference in gravitational pull between its near side and its far side. For a diffuse gas cloud like G2, lacking the structural cohesion of a solid body or a star, these forces were expected to be devastating. G2, estimated to be just 3 Earth masses and composed primarily of warm, ionized hydrogen, seemed especially vulnerable. It had no protective outer shell, no internal gravity strong enough to bind it tightly together, and no visible stellar core to provide structural integrity. It was essentially a blob of hot vapor drifting into the mouth of a lion. As it neared Sagittarius A, it would be pulled into a long, thin stream, its gas drawn into tendrils that would spiral inward, heat up, and eventually be consumed. Astrophysicists expected that this infall of material would trigger an energetic flare. When matter falls into a black hole, it doesn't just disappear instantly. Instead, it forms an accretion disk, a swirling, superheated ring of gas that radiates tremendous amounts of energy, especially in X-rays and infrared. The friction, collisions, and compression of gas particles in this disk can cause them to emit light thousands of times brighter than the original cloud itself. This is how some of the brightest phenomena in the universe, quasars and active galactic nuclei, are powered. Though Sagittarius A is typically dormant, astronomers hoped and expected that G2's destruction would act as a kind of wake-up call. The idea was that, even if the black hole only consumed a fraction of the cloud, the interaction would be enough to cause a visible flare. The core would light up in infrared and X-ray frequencies. Perhaps it would trigger outflows or jets. Perhaps the accretion rate would spike temporarily, giving scientists a rare window into how this relatively quiet black hole behaves when it feeds. Simulations backed up these expectations. Computer models showed G2 being stretched into a long, thin ribbon as it passed close to the black hole. The front edge would slow down slightly as it began to interact with the black hole's immediate environment, while the trailing edge, still falling in, would catch up, causing compression and shock waves. These interactions could lead to heating, fragmentation, and a rapid cascade of events, ultimately resulting in the cloud's partial or total destruction. The predicted timeline was precise. G2 would reach its pericenter, the closest point to Sagittarius A, around mid-2014. At that point, the greatest gravitational forces would act on it, and within weeks or months, the observable consequences would follow. Flares might emerge days after the Pericenter passage. The black hole might light up more than usual in the following months. All the observatories were on alert, including the Chandra X-ray Observatory, the Very Large Telescope, and the Keck Observatory, all hoping to catch the moment when the feeding began. The potential scientific payoff was enormous. Not only would this help scientists understand accretion processes in quiescent black holes, but it would also serve as a test for general relativity in a strong gravitational regime. It could offer data on how black holes interact with cold gas, how long accretion takes, and how jets or winds might be triggered. G2 was a gift, a fragile object whose destruction could illuminate some of the darkest questions in modern astrophysics. The excitement grew in the years leading up to the encounter. Conferences discussed the event at length. Papers speculated on every possible outcome. Would G2 form a temporary accretion disk? Would Sagittarius A flare like a mini-quasar? Would the gas be recycled into future star formation around the core, or disappear entirely into the void? But all of this anticipation was built on one crucial assumption, that G2 was exactly what it appeared to be, a free-floating, unbound gas cloud. Something without internal cohesion, without a core, without resilience. That assumption, as it turned out, would be the single greatest miscalculation in the entire saga. Because when 2014 finally arrived, and G2 made its dramatic flyby of Sagittarius A, the event that was expected to be a vivid spectacle became something else entirely. As the clock wound down toward G2's closest approach to Sagittarius A, the atmosphere in the global astronomy community grew palpably tense and electric. It was rare, exceedingly rare, for researchers to have advance notice of a potentially transformative cosmic event, one that could be observed in real time. Yet that's exactly what they had. The G2 cloud, a fragile-looking plume of warm gas just a few Earth masses in size, was plummeting into the most hostile region of the Milky Way. And for the first time, humanity had the technology and coordination to witness what would happen. Leading up to the anticipated 2014 encounter, teams around the world began intensive preparations. Telescopes were scheduled, observation runs were coordinated across continents, and models were constantly refined. The Very Large Telescope, VLT, in Chile and the W.M. Keck Observatory in Hawaii became ground zero for tracking G2's journey. Their powerful infrared instrumentation, Symphony on the VLT and Osiris on Keck, allowed astronomers to peer through the dense clouds of dust surrounding the galactic center, isolating the faint glow of G2 even as it slipped deeper into the gravitational pit of Sagittarius A. Each observing season brought sharper images and more precise measurements. Researchers tracked the elongation of G2's shape, its increasing velocity, and the subtle spectral shifts in the hydrogen emission lines that revealed the cloud's dynamic interactions with the environment. As G2 descended further toward the black hole, it began to stretch visibly. What had once appeared as a compact, nearly spherical object now looked more like a distorted smear, a streamer of gas unraveling under pressure. This confirmed what the models had predicted. Tidal forces were beginning to act on the cloud, drawing it out along its orbital path like taffy. In universities and observatories, the air buzzed with anticipation. Journal articles, preprints, and conference presentations poured in. Would G2 fragment before it reached Pericenter? Would it form an accretion disk? Would Sagittarius A suddenly flare up in a dramatic act of consumption? Astronomers were not only watching, they were racing against time to understand and simulate what they thought they were about to see. Multiple observatories collaborated to monitor G2 across the electromagnetic spectrum. While infrared provided the clearest spatial data, X-ray telescopes like NASA's Chandra and ESA's XMM Newton were on high alert, ready to detect any increase in high-energy radiation from Sagittarius A if the black hole began to feed. Even radio telescopes joined in, scanning for signs of synchrotron emissions that might indicate charged particles spiraling into magnetic fields. All eyes were on the galactic core. This was a planetary-scale stakeout. What made the event so thrilling wasn't just the raw data. It was the sense of being present at the edge of something fundamental. Black holes are elusive and enigmatic. You can't see them directly. You can only observe what happens near them. And for all the theories and computer simulations, there had never been a documented case of a free-floating cloud making a confirmed close approach to a supermassive black hole, let alone one so well tracked in advance. This was going to be a cosmic first. Night after night, observatories gathered spectra and images. Astronomers published position velocity diagrams showing how G2's gas shifted over time. Some portions redshifted as they fell away from us, others blue shifted as they came closer. These Doppler shifts offered a 3D view of the object's dynamics, revealing a twisted ribbon of gas plunging into a maelstrom. G2 was moving at breakneck speed, exceeding 9,000 kilometers per second, nearly 3% of the speed of light, as it approached the point of no return. Some scientists even made bold predictions that Sagittarius A would light up with a spectacular flare that could last for weeks, maybe even months, depending on how much of the cloud was accreted. The energy involved wouldn't just be bright, it would offer critical insights into how matter falls into black holes, how magnetic fields behave near the event horizon, and whether quiet black holes like Sagittarius A could be coaxed into revealing their true nature. The tension built steadily as G2 drew nearer and nearer to Pericenter. Observation teams were pulling long shifts, calibrating instruments, analyzing fresh data within hours of collection, and comparing notes across oceans. It was science at its most collaborative, and its most suspenseful. The sense of witnessing a live experiment conducted by nature itself was almost surreal. They weren't just passive observers, they were archivists of a moment in cosmic history. Then, finally, the fateful window of 2014 arrived. G2 reached the point in its orbit where it was closest to Sagittarius A, roughly 260 astronomical units, or about 24 billion kilometers. That may sound like a vast distance, but it placed G2 squarely inside the region of strongest gravitational influence, deep within the chaotic inner accretion zone. Astronomers held their breath. This was it. The moment of truth. Would the cloud disintegrate as expected? Would Sagittarius A awaken? Would the sky briefly erupt with energy from the galactic center? In the days and weeks that followed, the data streamed in, and the results stunned everyone. As 2014 unfolded, the astronomical world held its collective breath. After 3 years of meticulous tracking, G2 was now mere months, then weeks, away from the most perilous point in its orbit, Pericenter. This moment, the closest approach to Sagittarius A, was the critical juncture, the point at which all theoretical models and observational campaigns converged. Predictions of tidal shredding, fiery flares, and possible accretion activity all hinged on what would happen as G2 skimmed past the galaxy's central black hole at a distance of just 260 astronomical units. To put that distance into perspective, 260 Australian dollars is about 39 billion kilometers, or 6 times the distance from the Sun to Pluto. It sounds vast, but in terms of black hole proximity, it's practically brushing the edge of a monster's breath. For something as diffuse and lightweight as a gas cloud, being that close to a 4 million solar mass black hole is like dangling a spider web above a roaring furnace. Theoretical models unanimously agreed, G2 should begin disintegrating rapidly under the combined influence of gravitational tides, intense radiation, and interaction with the hot plasma that surrounds Sagittarius A. And yet, as G2 entered the pericenter phase of its orbit, something strange happened, nothing catastrophic. No explosion. No immediate flare. No obvious fragmentation. G2 passed the black hole and emerged on the other side of its trajectory, elongated, yes, distorted by gravitational shearing, but remarkably intact. At this stage, infrared spectra showed that G2 was stretched into a long filament. Instead of a compact, round blob, it now resembled a bright, wispy smear, a ribbon of gas pulled along the direction of its orbit. This stretching was expected. The tidal forces near a supermassive black hole can exert enough gravitational differential to pull even stars slightly out of shape. A gas cloud should be even more susceptible. And yet, despite this visible distortion, G2 held together far more than anyone had predicted. Its emission remained coherent. The cloud retained a measurable velocity profile. It was still very much a single entity. This was one of the most perplexing aspects of the encounter. Observations showed G2's velocity continuing to increase as it plunged into Pericenter, topping out at over 9,000 km per second, which is about 3% of the speed of light. The extreme Doppler shifts in its emission lines, especially bracket gamma and other hydrogen features, confirmed its speed and trajectory, showing both blue-shifted and red-shifted components as different parts of the cloud moved toward and away from Earth, respectively. These dual peaks in velocity offered a three-dimensional view of the object's movement through curved spacetime. During the Pericenter passage, astronomers expected G2's outer layers to be stripped off, dragged into spiral arms, and pulled inward to form a temporary accretion flow. They also expected Sagittarius A to respond to this feeding event with increased brightness, possibly even in the form of X-ray or infrared flares. But the black hole remained eerily quiet. No significant change in luminosity. No dramatic evidence of ingestion. It was as if Sagittarius A had barely noticed the encounter. This absence of expected drama did not disappoint astronomers, it bewildered them. The survival of G2 posed a direct challenge to many of the simulations that had anticipated a total or near-total disruption. It also raised questions about G2's internal structure. Perhaps it wasn't a simple gas cloud after all. Perhaps something was holding it together. Meanwhile, researchers continued to scrutinize every photon of data. Adaptive optics imaging from the VLT and Keck allowed high-resolution measurements of G2's morphology before, during, and after Pericenter. The results confirmed that while G2 had elongated, it hadn't fragmented into multiple smaller clouds, nor had it lost brightness in a way that suggested mass depletion. Its motion continued to trace a well-defined orbital path, and even after Pericenter, it appeared to be recoalescing slightly, suggesting that whatever tidal forces had acted on it were not enough to fully disperse it. Other instruments remained vigilant as well. X-ray observatories watched Sagittarius A with hopeful patience. They did detect some minor flaring in the months around Pericenter, but nothing on the scale that had been anticipated. There were no superflares, no sudden surges in accretion luminosity. If Sagittarius A had indeed consumed any part of G2, it did so quietly and with barely a flicker. This subdued aftermath led to a profound shift in interpretation. Perhaps G2 had a hidden core, something denser than gas, something capable of gravitational self-binding. Perhaps, as some had begun to whisper, it was not a mere gas cloud at all but rather a star enveloped in a shroud of gas and dust. A young star? A merged star? A stellar remnant cloaked in a dusty veil? The Pericenter moment hadn't just provided answers, it had deepened the mystery. Still, the event was a scientific triumph. The data collected during G2's Pericenter passage gave astronomers the most detailed, real-time look ever at a close encounter between a celestial object and a supermassive black hole. It offered new constraints on how black holes accrete matter, how gas behaves in extreme gravitational fields, and how the galactic center environment shapes the fate of objects that venture too close. And most importantly, it redefined what was possible. G2 had walked into the dragon's lair and emerged, not untouched, but unbeaten. In surviving the gravitational maw of Sagittarius A, it had rewritten the rulebook. Astronomers no longer had the luxury of assuming that anything faint and fuzzy near a black hole was doomed. Now they had to account for resilience. As G2 rounded its closest point to Sagittarius A and continued its path around the galactic center, astronomers continued monitoring it obsessively, anxious to understand the true nature of what they had just witnessed. The cloud's survival, still baffling, did not mean it had emerged unscathed. On the contrary, its transformation was obvious and dramatic. Observations made during and after the Pericenter moment showed G2's structure being elongated and distorted in a way that was consistent with strong tidal forces acting on a loose, extended object. Yet again, the cloud defied destruction. This elongation, known as tidal stretching, occurs when different parts of an object experience varying degrees of gravitational pull. For G2, this meant the part of the cloud closer to the black hole was tugged more forcefully than the trailing end, which resulted in the cloud being stretched along its orbital path. From a once compact, roundish object, G2 became a streak, its gas trailing behind it in a narrow filament, not unlike a celestial comet with an impossibly long tail. The Very Large Telescope and Keck Observatory delivered high-resolution images and spectroscopic data that captured this process in remarkable detail. The emission lines from hydrogen and helium, especially the bracket gamma line, showed distinct shifts as parts of the cloud moved toward and away from us. This motion allowed scientists to construct velocity maps of the cloud, revealing a complex flow of material, some being drawn forward, some lagging behind. These maps were essentially three-dimensional fingerprints of how gravity was sculpting the cloud in real time. But what stood out the most was not just how G2 was changing, but how coherent it remained despite that change. Simulations had predicted a more catastrophic outcome: complete fragmentation, chaotic spiraling, and rapid accretion of torn-off filaments. Instead, while G2 did stretch dramatically, it still showed signs of internal integrity. There were no large-scale breakups, no sudden drops in luminosity, and no loss of overall mass that could be confirmed. It was like watching a balloon being pulled into a long sausage shape, deformed, but still whole. In many ways, this behavior resembled what scientists call tidal stripping without disruption. That is, the outer edges of G2 were clearly affected by the gravitational pull of Sagittarius A, and some gas may very well have been lost during the encounter. However, the main body of the cloud clung together. This was deeply surprising. It hinted at one of two possibilities: either the gas within G2 was more tightly bound than previously assumed, or there was something at its core helping to keep it together. Supporting this, researchers noticed that G2's post-Pericenter brightness did not fade as quickly as a gas-only cloud would after such an encounter. Instead, it maintained a relatively stable luminosity, suggesting that the cloud was not just a passive puff of gas being sheared apart, but possibly an active system with internal dynamics. Moreover, the tail of gas stretching behind G2 did not fan out chaotically. It followed the same general orbital curve, implying that whatever shedding had occurred did so in a controlled manner. Tidal stretching also offered a rare, real-world confirmation of theoretical gravitational dynamics in the strong field regime. Observing G2 elongate in the presence of Sagittarius A provided astronomers with a unique dataset for modeling how gas clouds and diffuse matter interact with supermassive black holes. This interaction is often assumed to lead inevitably to accretion and flaring, but G2 showed that the actual process can be far more complex. Some gas can be stripped while the rest continues on its path, perhaps to orbit for decades or even centuries before another close approach. Infrared imaging revealed that G2's elongated shape persisted well after its closest approach, with some signs of the leading edge continuing to move forward at high velocity, while the rear slowly caught up. This differential motion, caused by the uneven gravitational force across the cloud's length, not only elongated it further but may have temporarily increased internal pressure and heating. These conditions could explain why some emission lines grew stronger post-Pericenter. It wasn't just the black hole's influence, but also G2's own internal compression that contributed to the radiation astronomers observed. Still, the fact that G2 did not completely unravel became the central mystery. In previous observations of tidal disruption events in other galaxies, we've seen stars shredded into arcs of light. We've seen black holes flare in dramatic bursts after consuming disrupted material. But G2, light, dusty, and ionized, should have been even more fragile than a star. And yet, its survival demanded an explanation beyond simple gas dynamics. Some researchers began to propose that G2 might have a gravitational center of its own, perhaps a star or compact object buried deep in its dusty cocoon. If such a core existed, it would act like an anchor during the tidal encounter, holding the cloud together despite the external stretching. Like a kite tethered by a string, the gas would elongate, flutter, and distort, but it wouldn't simply fly apart. This idea would soon become the focus of intense debate and analysis, leading to a host of new hypotheses. But even without a definitive answer at that moment, the tidal stretching phase of G2's journey offered one of the most visually compelling and physically illuminating episodes in the saga. It was a front-row seat to gravitational warfare, the black hole pulling with all its might, and the cloud resisting with whatever hidden structure or coherence it possessed. That resistance, that refusal to tear apart entirely, told us something profound, that the dynamics near a black hole are not just about destruction. They are also about survival, about the subtle balancing of forces in a cosmic tug-of-war where even the most fragile-seeming objects may endure. When the dust, quite literally, settled after G2's dramatic near-death experience with the Milky Way's central black hole, astronomers around the world found themselves confronting a reality they hadn't anticipated. G2, the cloud that was expected to be ripped apart, devoured, and turned into a radiant feast for Sagittarius A, had done something far more provocative. It survived. Not partially, not barely, fully. It continued its orbit around the galactic center, as if it had merely skimmed past danger, not plunged headfirst into it. This was not just unexpected. It was a direct contradiction of nearly every simulation and theoretical prediction made in the years prior. Why? That was now the urgent question, one that demanded a reevaluation of everything astronomers thought they knew about the galactic center, gas cloud dynamics, and black hole feeding behavior. Initially, theories had operated on the assumption that G2 was a free-floating, unbound gas cloud, a dusty, ionized ball of mass totaling roughly 3 times that of Earth, with no internal gravity of its own. By all known laws of physics, such an object should not survive a $260 pass near a 4 million solar mass black hole. The tidal forces should have shredded it. The accretion flow should have dragged it in. At the very least, it should have left behind a trail of glowing fragments, or disappeared entirely into Sagittarius A's gravitational mouth. But none of that happened. Instead, what astronomers saw was an object that passed through the black hole's intense gravitational field and came out the other side with its integrity largely intact. It stretched, yes. It distorted. But it did not break apart or get swallowed. Even more curious, the black hole itself showed no significant response. No violent flare. No sudden burst of X-ray or infrared radiation. No signs that it had gorged itself on incoming matter. The galactic monster, it seemed, hadn't fed at all. This left scientists with one conclusion: G2 was not what it appeared to be. What had been modeled as a homogeneous, weakly bound gas cloud must instead possess some form of internal cohesion. That led to the dominant new hypothesis, one that would redefine the conversation entirely. Perhaps G2 wasn't just a gas cloud. Perhaps it contained a central object, a star. If G2 were not merely a diffuse collection of gas but rather a stellar object shrouded in a thick cocoon of gas and dust, the story would suddenly make much more sense. The central star's own gravity could hold the surrounding material together, resisting the disruptive tidal forces of the black hole. The gas might distort, trail, or even shed slightly, but the system as a whole would remain gravitationally bound. That meant G2's survival was not a miraculous escape. It was the result of a hidden anchor that had never been accounted for. This explanation, often referred to as the hidden star hypothesis, became the focus of intense study in the years following Pericenter. It also reframed G2's journey as a revelation rather than an anomaly. If G2 were a young star with a thick envelope, possibly still accreting material or recently formed, it would explain its unusual appearance, its infrared brightness, and its resistance to tidal disruption. Some researchers took the theory a step further. What if G2 was not just a young star, but the remnant of a stellar merger? In the chaotic core of the galaxy, where stars are packed densely together and gravitational interactions are frequent, 2 stars could collide or merge, creating a swollen, dust-enshrouded object with unstable outer layers. Such a star would naturally emit strong infrared light due to its dusty shell, and its recent violent formation could explain its erratic orbit and structure. But even without certainty about its origins, G2's survival forced astronomers to revisit many long-held assumptions. Chief among them was the idea that the environment near a supermassive black hole is inevitably hostile to small objects. G2 demonstrated that survival was not only possible, it could be stable, at least over short timescales. The implications of this extended beyond just G2. It meant that other faint, dusty sources near the galactic center might also harbor hidden stars or complex histories. It suggested that the galactic core, while chaotic, was not entirely lethal. And it hinted at a deeper mystery, just how many such objects were quietly orbiting in that dangerous region, masquerading as fragile gas clouds? Another surprise was the black hole's behavior. Why had Sagittarius A not flared in response to G2's passage? The best answer, in hindsight, was that G2 simply didn't offer much in the way of food. Its dense core, assuming it had one, remained bound, and its outer gas was not sufficiently disrupted to become accreted. In effect, it passed through the black hole's feeding zone without shedding enough material to trigger a response. This challenged the notion that all infalling matter near a black hole will inevitably be devoured or cause energetic outbursts. G2's quiet survival revealed an uncomfortable truth: supermassive black holes may be far pickier eaters than we thought. Just because an object enters the kill zone doesn't mean it becomes a meal. This realization has significant implications for how we interpret quiescent galaxies and black holes that don't show much activity. Perhaps they're surrounded by potential meals, but none of them meet the criteria for ingestion. In the case of G2, it was like a bird flying past the mouth of a lion, close, fleeting, but never quite within reach. The sheer surprise of G2's continued existence turned what was expected to be a destructive encounter into one of the most instructive cosmic moments of the decade. It highlighted the limits of our models, the hidden complexity of galactic dynamics, and the possibility that the universe often hides its most remarkable truths behind layers of dust and deception. G2 didn't just survive, it told us, in its own quiet way, that we still have much to learn about the forces governing the heart of our galaxy. As the post-Pericenter dust began to settle, figuratively and literally, astronomers found themselves confronted by a question that refused to go away: what exactly is G2? The initial assumption had always been that it was a relatively simple object, a clump of warm, ionized gas, loosely held together, drifting through the galactic center. But after its survival of what should have been a lethal encounter with Sagittarius A, the sheer improbability of that outcome began to shift the conversation. G2 had not behaved like a gas cloud. It hadn't disintegrated. It hadn't collapsed inward into the black hole. It hadn't lit up the galactic center with a feeding flare. Instead, it elongated, evolved, and emerged mostly intact. This left the field with a deepening suspicion. Maybe G2 wasn't just a gas cloud after all. Maybe it was something far more complex. The idea that G2 might be more than just a floating plume of dust and hydrogen began to gain serious traction. It would explain almost everything that had gone wrong with earlier predictions. A star hidden at the center of the gas cloud could have provided the gravitational glue necessary to resist tidal disruption. It could have explained the coherence of the object's post-Pericenter motion, the relative consistency of its brightness, and even its emission spectra, which remained strong in hydrogen recombination lines. It would also explain why Sagittarius A didn't seem particularly interested in feeding. The cloud hadn't been shredded into bite-sized pieces. It had held together, thanks to a mass hidden at its core. But this posed a fresh challenge. If G2 had a star at its heart, why hadn't we seen it? The galactic center is one of the most dust-obscured regions in the entire sky. Visible light cannot penetrate it, which is why infrared observations are crucial. And G2 had been studied almost exclusively in infrared from the beginning. Yet the object had never shown the typical signature of a naked star. No sharp spectral lines from a stellar photosphere, no strong blackbody continuum typical of a main sequence or giant star. The emission was dominated by gas, not stellar light. This led to the next natural assumption: the putative star must be deeply embedded within a thick envelope of gas and dust. In other words, the star wasn't missing, it was hidden, smothered by a cloud so dense and warm that its light was completely veiled. It would be like trying to detect the glow of a firefly inside a thick fog bank, technically visible, but washed out by the haze. If G2 was indeed a star wrapped in gas, then it became a member of a much more complex and intriguing class of objects. Astronomers began drawing comparisons to young stellar objects, stars that are still forming, and therefore still surrounded by the remnants of their birth clouds. These stars are known to be infrared bright, just like G2. They are also messy, unstable, and hard to study in detail. But in G2's case, there was no evidence of star formation activity near its orbit. The galactic center is a hostile place, not an ideal nursery for stars in their earliest phases. Which pushed the discussion toward another hypothesis. Perhaps G2 was not young, but scarred. Perhaps it was the result of violence. That idea, that G2 could be the aftermath of a stellar merger, gained rapid popularity. In this scenario, two stars, perhaps part of a tight binary system, collided or coalesced due to gravitational perturbations near the galactic center. The result would be a newly merged star, bloated and unstable, enveloped in the gas and dust thrown off by the collision. Such a star would be infrared luminous, masked by an expanding shell of matter, and exhibit irregular behavior. It might not look like a conventional star at all. It might look, exactly, like G2. Support for this model came from orbital dynamics. G2's path around Sagittarius A is highly eccentric, with an elongated trajectory that brought it perilously close to the black hole before swinging it back out again. That kind of orbit is not typical for a newly born star, but it could plausibly be inherited by the remnant of a disrupted binary system. In fact, gravitational interactions in the galactic core are known to eject stars at high speeds, or to fling them into wildly erratic orbits. A merger could have been triggered by such an encounter, resulting in a cloud-shrouded survivor set on a death-defying course. Still, even as the star hypothesis gained favor, some astronomers remained cautious. The nature of G2's infrared emission, while consistent with dusty gas, still lacked clear stellar fingerprints. And the object didn't show strong signs of variability or outbursts that one might expect from a recently merged or accreting star. Was the cloud stable enough for a star to survive in it for years? Could the gas have cooled and settled into a disk around the core, or was it still expanding outward? These questions were not easy to answer. The limits of resolution near the galactic center, even for the best instruments on Earth, made it difficult to peer inside G2's foggy shell. We could measure its size, velocity, brightness, and spectral lines, but we couldn't yet unambiguously identify a stellar core. We were left with indirect evidence. The cloud survived a tidal onslaught that should have torn it apart. That survival implied structure, and structure implied gravity. Gravity, in turn, implied mass. And where there is mass, there may well be a star. So G2 became more than an object of curiosity. It became a mystery with layers, perhaps a stellar object masquerading as a gas cloud, perhaps the wreckage of a recent merger, perhaps something stranger still. Whatever it was, it had defied expectations, rewritten predictions, and opened a floodgate of theoretical reevaluation. No longer was it safe to assume that faint, dusty blobs near the galactic center were simple gas clouds. G2 had taught us that appearances can be profoundly deceptive, especially in a region where gravity bends not only space and time, but the rules we thought we understood. The growing suspicion that G2 was not a mere gas cloud but a more complex system found a focused and compelling formulation in what became known as the hidden star hypothesis. This idea proposed that at the heart of the G2 object lies a compact, dense star, possibly a young, low-mass stellar object, enshrouded in a thick envelope of gas and dust. Such an internal structure would neatly account for G2's coherence and survival during its close encounter with Sagittarius A, and explain several of its baffling observational features. At first glance, this idea may seem speculative, but there is a strong physical rationale behind it. When an extended gas cloud encounters the immense tidal forces of a supermassive black hole, it lacks the self-gravity to resist being pulled apart. Yet G2 had done exactly that, endured, stretched but intact. This survival signaled the presence of internal binding. The only plausible explanation was that some kind of gravitational core existed within the cloud, exerting enough influence to prevent complete dissipation. In essence, the gas had an anchor. If a star truly resides at the center of G2, it would explain why the object continued to follow a compact, elliptical orbit even after Pericenter. Gas alone, once stretched and stripped, would either fall into the black hole or disperse into space. But the G2 object retained a consistent, trackable path, clear evidence that some substantial mass was guiding its motion, not just momentum. In this light, the cloud was not a solitary wanderer. It was a cloaked voyager, hiding its true form behind a luminous veil. The physical properties of G2 also lent credibility to the hidden star theory. Its emission was dominated by infrared wavelengths, consistent with the thermal signature of warm dust and ionized gas. But this infrared glow didn't behave like the radiation from a transient gas stream. It was relatively steady, stable, and localized. That sort of consistent emission suggests a central heat source, like a star, continuously exciting the surrounding gas. Without such a core, the dust and gas would cool and fade rapidly, especially after escaping the intense radiation fields of Sagittarius A. Yet G2 remained visible and relatively unchanged in brightness for years after its close pass, defying the timeline predicted for an unbound cloud. This hypothesis also gained strength from comparisons to similar astrophysical phenomena. In other parts of the galaxy, particularly in regions of dense stellar interaction or star formation, astronomers have observed stellar masqueraders, young stars still cloaked in birth clouds, or merger products cloaked in ejected gas. These objects often appear as diffuse, glowing blobs in infrared surveys, lacking distinct stellar signatures but emitting persistently nonetheless. Some are protostars, others are post-merger giants. In both cases, the presence of gas doesn't negate the star, it hides it. In G2's case, the hypothesis suggested a young, relatively low-mass star, perhaps less than 1 solar mass, wrapped in a cocoon of warm gas and dust. The envelope may have been created during the star's formation, or more dramatically, as a result of a stellar merger. Either scenario implied that G2's dusty veil was not a permanent feature but a transient phase in a longer stellar evolution story. Several lines of inquiry supported this model. For one, G2's spectrum exhibited strong hydrogen recombination lines, especially bracket gamma, which typically arise when ionized gas is being photoexcited by a strong energy source. While Sagittarius A itself could account for some of the ionization, the persistence and shape of these lines hinted at a more localized origin. A star buried in the cloud, emitting ultraviolet and soft X-ray radiation, would naturally ionize the surrounding hydrogen and produce the observed emission profile. Moreover, high-resolution imaging showed that G2's morphology remained compact post-Pericenter, despite tidal stretching. While the outer portions trailed and elongated, the core remained relatively symmetric. If G2 were merely gas, the core should have diffused. Its retention of shape hinted at gravitational self-containment, again pointing to a central stellar mass. This idea wasn't just a convenient patch, it made predictions. If G2 had a star inside, then in the years following its close approach, the gas envelope should begin to thin. As the cloud dissipated or was stripped away, the star should gradually emerge, becoming more visible in infrared and potentially even in shorter wavelengths, depending on the thickness of the remaining dust. And indeed, subsequent observations began to reveal hints that the object's profile was changing. The emission remained, but some observers noted a slow shift in the spectral lines, suggesting a possible decline in the envelope's density. If this trend continued, it would support the idea that we are watching a transient veil slowly lifting, like fog retreating to reveal a mountain beneath. But the hidden star hypothesis raised deeper questions too. If G2 was not unique, if it was part of a population of shrouded stars near the galactic center, how many more such objects were there? Could the so-called G objects, a group of similar, dusty infrared sources found in the same region, also be stars hidden in gas envelopes? Was there a whole class of cloaked stars, moving around Sagittarius A, each mimicking the appearance of gas clouds? These questions would steer the next decade of research toward an entirely new realm of galactic center astrophysics. G2 was no longer just a curiosity, it had become a prototype. And the hidden star hypothesis had reframed not just one object, but the landscape of an entire region. While the hidden star hypothesis offered one plausible solution to G2's puzzling survival, it opened the door to an even more dramatic scenario, one that pushed beyond the idea of a simple young star and ventured into the domain of celestial violence. What if G2 wasn't just a star wrapped in gas and dust? What if that gas and dust were the result of a recent and catastrophic union, a stellar merger? This theory, first suggested shortly after G2's surprising resilience became clear, added a thrilling new twist to its mystery. In the dense, dynamic environment of the galactic center, stars are not isolated entities floating peacefully through space. They are packed into tight orbits, sometimes separated by just a few light days. This gravitational crowding is the perfect setting for chaos. When binaries, pairs of stars orbiting one another, drift too close to Sagittarius A or interact with other nearby stars, their orbits can become unstable. In such situations, one star can be ejected while the other plunges inward, or the pair can spiral together in a final, fatal embrace. A merger between two stars releases an enormous amount of energy, and typically results in a single, bloated stellar object surrounded by a cocoon of gas and dust. This aftermath glows brightly in the infrared and can remain shrouded for years or even decades. If such a merger occurred within the last few decades near the galactic center, the resulting object would appear exactly like G2, warm, luminous, dust enshrouded, and unusually resilient. This theory would explain many of G2's most curious traits. Its elongated, dusty envelope? That could be leftover material ejected during the violent merging event. Its survival of tidal forces? A newly formed, relatively massive central object could bind the surrounding gas tightly enough to resist disruption. Its lack of a stellar signature in traditional spectra? The dust cloud would easily obscure any direct light from the star, leaving only the glow of excited gas. One of the most compelling pieces of circumstantial evidence for the stellar merger theory came from the shape of G2's orbit. It wasn't a lazy, circular path but a wild, elongated loop plunging deeply into the black hole's gravitational well. Such a trajectory isn't typical for long-lived, stable objects but fits well with the outcome of a recent dynamical event, especially one involving multiple bodies. If two stars in a binary system merged as a result of gravitational perturbation, perhaps after a close encounter with another star or with Sagittarius A itself, the newly created object could have been flung into a fresh, high-eccentricity orbit like the one observed for G2. This possibility wasn't just speculation. Stellar mergers have been observed elsewhere in the galaxy. In 2002, for example, astronomers witnessed a red nova eruption in the constellation Monoceros, later attributed to a stellar collision. That event, known as V838 Monocerotis, produced a spectacular light echo and a dusty shroud that lingered for years. If such a collision happened near the galactic center, hidden behind thick clouds of interstellar dust, it might escape notice until its aftermath became visible in the infrared, just as with G2. What made the stellar merger hypothesis particularly appealing was that it not only accounted for G2's behavior, but it also fit within a broader framework of galactic center dynamics. The region around Sagittarius A is chaotic, turbulent, and densely populated with stars, compact objects, and gravitational perturbations. Encounters between stars, especially binaries, are not just possible, they're likely. In fact, the very presence of stars in close orbit around Sagittarius A implies a long history of scattering events, disruptions, and interactions. According to simulations, binary mergers near supermassive black holes can occur more frequently than in quieter regions of space. When a binary system ventures too close to the black hole, its gravitational grip can be broken. One star may be captured, and the other flung away at high velocity, a process known as the Hill's mechanism. But under certain conditions, the stars may not separate cleanly. Instead, orbital energy can be dissipated as heat and angular momentum, causing the stars to spiral inward and merge. This would result in a single, hot, swollen object, enveloped in the material thrown off during the event. A dusty cloud surrounding a newly formed star. An object just like G2. If G2 was the product of such a merger, it may be only a temporary object in its current state. Over time, the dust would settle or disperse, revealing the central star. The infrared glow would fade. Eventually, G2 might appear to vanish, not because it's been destroyed, but because it has evolved into something quieter, more typical, a star indistinguishable from others near the galactic core. But the implications go further. If G2 is a stellar merger, how many other G objects are too? G1, G3, G4, G5, G6. These similarly dusty, infrared bright entities also orbit near the galactic center, with some showing similar elongation and spectral features. Could they all be merger remnants? If so, the population of cloak stars near Sagittarius A might represent an entire class of post-merger objects, waiting to be unmasked. This idea reshapes how we interpret the galactic core. Rather than being solely a region of high-energy astrophysics, accretion disks, relativistic jets, and black hole flares, it may also be a quiet graveyard of stellar wreckage and rebirth. The center of our galaxy may be less a devouring void and more a cosmic crucible, forging strange, short-lived objects like G2 in the wake of stellar collisions. The stellar merger theory doesn't just explain G2, it enriches the entire narrative. It paints a portrait of a galactic center that is both more violent and more fertile than we imagined. It is a place where stars don't just die, but sometimes, spectacularly, become one. Of all the astonishing twists in the G2 saga, perhaps none was as counterintuitive, or as revealing, as what didn't happen. As G2 swept past the Milky Way's central supermassive black hole, Sagittarius A, scientists worldwide were not merely expecting a spectacle, they were counting on it. Years of simulations, theoretical modeling, and speculative forecasts had pointed to one likely outcome: G2's gas would be stripped, drawn into the black hole's accretion zone, and trigger a brilliant flare, perhaps the brightest in recorded history for this usually quiet cosmic giant. Yet, as the cloud made its closest approach, something remarkable occurred. Or rather, didn't occur. Sagittarius A stayed calm. The sky didn't erupt in X-rays. There was no sudden outburst of infrared fire. The beast stayed asleep. And the cloud moved on. To understand why this was so surprising, we must first revisit the expectation that surrounded G2's encounter. Black holes, particularly those as massive as Sagittarius A, are known to feed on nearby matter when it strays too close. Gas clouds make ideal snacks. As they approach the event horizon, tidal forces stretch them, magnetic fields entangle them, and friction from surrounding material causes them to heat up, glow, and fall inward. This process is what powers some of the brightest objects in the universe. Active galactic nuclei and quasars are just supermassive black holes caught in a feeding frenzy. Sagittarius A, by contrast, is unusually quiet. It emits only faint radio and X-ray signals, and for much of modern astronomy's observational history, it has been relatively dormant. But the arrival of G2 was thought to be the spark that would awaken the monster. The logic was simple: G2's gas, encountering the black hole's immense gravitational well, would be funneled into the accretion zone and rapidly consumed. This process, even if modest by the standards of active galaxies, would still result in a major flare, an astronomical firework visible across the electromagnetic spectrum. Observatories on Earth and in space aligned their schedules accordingly, eager to catch Sagittarius A in the act. What they got instead was near total silence. This silence raised a serious question: why didn't Sagittarius A flare? Several explanations emerged, each one probing deeper into the physics of black hole accretion and the peculiar nature of G2. The first possibility was deceptively simple: perhaps G2 didn't lose enough material. While some tidal stretching and gas trailing were observed, the amount of mass actually stripped from G2 and directed towards Sagittarius A may have been negligible. If the bulk of the cloud remained gravitationally bound, either through self-coherence, or due to the presence of a central star, then there simply wasn't enough free-floating gas available to trigger a flare. In this interpretation, G2's compactness was its shield. It passed through the black hole's domain like a stone skipping over water, close, but never engulfed. Another factor could lie in the timing and behavior of accretion itself. The process of matter falling into a black hole isn't instantaneous. Gas that gets stripped from an object doesn't simply plunge inward and vanish. It often spirals through a complex, turbulent disk. This accretion process can take months or even years, depending on the density, angular momentum, and temperature of the infalling material. If G2 did lose gas, but that gas is still orbiting in the outer fringes of Sagittarius A's accretion zone, it may yet produce a delayed flare, one that could happen years after the initial encounter. However, more than a decade has passed since G2's Pericenter, and no such flare has emerged. The silence, if anything, has only grown more puzzling. This led scientists to consider another, more intriguing explanation. Perhaps Sagittarius A is not merely dormant, but starved. While it is certainly massive, the environment around it may not be conducive to regular feeding. Accretion flows, magnetic turbulence, and angular momentum barriers might all work together to prevent even available material from falling in. In such a model, Sagittarius A is less like a gluttonous beast waiting to pounce and more like a picky eater surrounded by unappetizing crumbs. G2, while close and seemingly vulnerable, simply didn't meet the criteria for consumption. This interpretation reshapes our entire understanding of what it means to feed a black hole. For decades, astronomers assumed that any object coming close to the event horizon, especially a gaseous one, would be shredded and consumed. But G2 challenged that view. It proved that close proximity alone isn't enough. Other factors, density, composition, structure, and trajectory, all play critical roles in determining whether a black hole will react or ignore. Some propose that Sagittarius A might possess a hot, radiatively inefficient accretion flow, a structure that prevents cool gas like G2's envelope from integrating easily. In this scenario, the gas surrounding the black hole is so hot and diffused that it acts like a pressure barrier, keeping new material at bay. Rather than spiraling inward, the cooler gas from G2 might have been deflected, heated, or dispersed before it could settle into the black hole's feeding zone. This paints Sagittarius A not as a vacuum cleaner, but as a fortress, surrounded by walls of turbulent plasma that repel most intruders. Still others pointed to the lack of magnetic coupling between G2 and the black hole's environment. Strong magnetic fields can help channel gas inward by removing angular momentum and promoting inflow. If G2 lacked the right alignment, or if its internal magnetic structure was weak, then its gas might have simply brushed against the black hole's outer defenses before being swept away or left adrift. Yet another angle explored the role of angular momentum itself. For gas to fall into a black hole, it must lose much of its rotational energy. If G2's gas maintained too much angular momentum, perhaps inherited from the orbital motion of the cloud or a central star, then it wouldn't spiral inward. Instead, it would form a wide arc and miss the accretion zone entirely, looping around Sagittarius A like a comet around the Sun. In truth, the answer may lie in a combination of all these effects: insufficient mass loss, a cohesive internal structure, angular momentum barriers, hot accretion flow shielding, and a magnetic mismatch. Each element helps to explain why a cloud so close to death simply passed by, untouched. Whatever the cause, the non-event of G2's encounter became one of its most scientifically valuable outcomes. It forced astronomers to abandon overly simplistic models of black hole feeding and adopt a more nuanced understanding. It also reminded the scientific community that sometimes, the silence in the cosmos can speak louder than an explosion. G2 didn't feed the beast, but in its restraint, it revealed the limits of our expectations, and opened a new era of questions about what it takes to truly awaken a giant. The question that lingered in the void after G2's silent passage past Sagittarius A wasn't merely, "Why didn't the black hole react?" but something more subtle and revealing. Is Sagittarius A even hungry? For decades, black holes have occupied a primal corner of our imagination, as cosmic devourers, unrelenting consumers of matter and light. But G2's survival, paired with the underwhelming response from the galactic center, forced astronomers to entertain a radical new possibility. Maybe our galaxy's central black hole is not just quiet, it's actively fasting. On paper, Sagittarius A should be feasting. It sits at the very heart of the Milky Way, surrounded by a dense cluster of stars, stellar winds, magnetic fields, and drifting interstellar gas. The gravitational pull it exerts is tremendous, powerful enough to shape the orbits of stars within a light-month radius. And yet, for a black hole with over 4 million times the mass of our Sun, it emits astonishingly little. Its X-ray and radio output are minuscule compared to what we'd expect from a black hole of this scale. And now, G2 had passed within a mere 260 astronomical units, roughly 40 billion kilometers, of this monster, trailing gas, glowing in the infrared, and carrying the potential energy of an approaching meal. And still, nothing. No flare. No accretion event. Just eerie calm. So why is Sagittarius A so underfed? One of the first ideas scientists considered was the nature of accretion itself. Feeding a black hole is not as simple as tossing matter into a gravitational well. Matter must lose angular momentum, heat up, and become part of an accretion disk, a tightly bound structure where gas slowly spirals inward over time. If there's too much angular momentum, the material simply slingshots around the black hole and is ejected. If there's not enough gravitational binding, it disperses before reaching the point of no return. In short, black holes are actually hard to feed. In the case of Sagittarius A, the region surrounding it may be even more difficult to penetrate than expected. Observations suggest that the black hole is surrounded by a hot, turbulent, low-density accretion flow known as a radiatively inefficient accretion flow, RIF. In a RIF, much of the gas never cools enough to settle into an orderly disk. Instead, it swirls and churns like a storm, highly energetic, but poor at transferring matter inward. If G2's gas encountered this environment, it may have simply bounced off, dissipated, or been absorbed into the outer edges without ever reaching the inner feeding zone. There's also the problem of thermal mismatch. The gas in G2 is relatively cool, warm enough to emit an infrared, but not hot by galactic core standards. When this cooler material encounters the hotter, more ionized gas near the black hole, it can become unstable. Rather than being smoothly integrated, it can be disrupted, stripped, or deflected. This process is somewhat analogous to trying to mix cold cream into a pot of boiling water. The temperature difference creates turbulence, resistance, and separation. But beyond the physics of gas dynamics lies a more profound realization. Perhaps Sagittarius A is in a fundamentally different state than many of its more active cousins in other galaxies. Some galaxies have blazing quasars at their centers, black holes that are gorging on matter at nearly the Eddington limit, shining like beacons across the universe. Others are moderately active, with regular outbursts, jets, and flares. And then there's our galaxy, home to a supermassive black hole that behaves like a recluse. This contrast begs a deeper question. Why are some black holes ravenous, while others starve? One key factor is supply chain. In more active galaxies, gas is often funneled toward the center by large-scale galactic events, mergers with other galaxies, bars in the galactic disk that transport material inward, or frequent starbursts that inject fresh gas into the core. The Milky Way, by contrast, is relatively quiet. Its central bar is weak, its merger history mild, and its supply of cool gas limited. Even the powerful stellar winds from nearby massive stars might not be enough to form a thick, cold accretion disk. Sagittarius A may be simply starving not because it refuses food, but because it lives in a cosmic desert. The idea that our galaxy's black hole is on a long-term diet reframes our understanding of its behavior. It suggests that inactivity is not a fluke, it's a phase. Black holes don't need to be permanently active to grow. They can pass through epochs of dormancy, punctuated by brief feasting episodes triggered by special events, like the infall of a dense gas cloud, or the tidal disruption of a wandering star. Perhaps millions of years ago, Sagittarius A blazed like a quasar. Perhaps millions of years from now, it will again. But today, we live in a rare era of cosmic quietude. What's more, This dormancy has allowed astronomers to study the region around Sagittarius A with unparalleled clarity. In an active galactic nucleus, the intense radiation from the central black hole often drowns out nearby stars, clouds, and structures. But in our case, the relative faintness of Sagittarius A allows instruments like the Keck Observatory and the Very Large Telescope to track stars in tight orbits, resolve gas motions, and peer deep into the galactic center with precision. It's as though the beast sleeps just long enough to let us study the conditions that shape it. And so, the question, why didn't it eat? May have a simple answer: because it wasn't time. G2 may have been too coherent, too dense, or simply too misaligned to be digested. Or perhaps the black hole is simply full, or at least not desperate. This paints a picture of black holes not as indiscriminate destroyers, but as complex participants in a dynamic cosmic environment. They feed when conditions are right. They flare when the menu allows. And sometimes they wait. In this context, Sagittarius A is not broken. It's biding its time. A monster on a diet, not from restraint, but from cosmic circumstance. In the aftermath of G2's unexpected survival, astronomers turned their eyes to the years that followed with renewed fascination. The close pass had come and gone. The anticipated fireworks had failed to materialize. And yet, something even more compelling was beginning to unfold. G2 did not dissipate. It did not collapse, nor did it vanish into the background clutter of the galactic center. Instead, it lingered, persistent, glowing, and still very much intact. This baffling endurance became the subject of intense observation, as astronomers sought to understand what G2 was becoming in the wake of its near-death experience. Using the same powerful instruments that tracked its initial approach, chiefly the Very Large Telescope, VLT, in Chile and the twin Keck telescopes in Hawaii, scientists continued to monitor the object year after year. Observations were primarily carried out in the infrared, the only window that could penetrate the thick dust obscuring the galactic core. What they found challenged expectations all over again. First and foremost, G2 remained visible. This was, in itself, a surprise. If G2 had been a simple, diffuse cloud of gas, then the gravitational stretching it endured near Pericenter should have disrupted its cohesion. The material would have elongated into a stream, losing density and fading from detectability. But post-2014 data showed that while G2 had elongated somewhat during the pass, the core structure of the object retained a surprising degree of compactness. It continued to emit strong bracket gamma hydrogen recombination lines, clear signatures of ionized gas illuminated by some internal energy source. This was not the aftermath of destruction. It was the persistence of identity. More intriguing still, the motion of G2 after Pericenter remained consistent with an object on a bound, elliptical orbit around Sagittarius A. Had the cloud disintegrated, the dispersed gas would have followed complex, sheared trajectories, quickly becoming indistinguishable from the surrounding environment. But the continued tracking of G2 showed it retained orbital coherence. It was behaving more like a single object with internal gravitational binding than a mass of shredded debris. This longevity lent further weight to the theories already emerging, that G2 was not simply a gas cloud, but something more structured. Perhaps it harbored a star. Perhaps it was the product of a recent stellar merger. Either way, the years following Pericenter did not witness the fading of a doomed object. Instead, they revealed the evolution of something alive, something dynamic. In fact, as astronomers watched G2, they noticed its brightness and emission characteristics changed gradually over time. While still luminous, its infrared emission began to decrease slightly, suggesting a thinning or dispersal of the outer layers of its gaseous envelope. This slow transformation aligned with predictions made under the hidden star and stellar merger hypotheses. If G2 contained a central stellar object, then the gas surrounding it would eventually cool, expand, or get stripped away by stellar winds and radiation. Over years or decades, the veil would lift, and the star would emerge more clearly. This gradual unveiling became one of the key goals of ongoing observation campaigns. Researchers hoped that by tracking the subtle evolution of G2's spectral lines, shape, and motion, they could eventually glimpse the true source at its heart. Every year offered a new data point, a chance to catch the transformation in action. Was G2 fading? Was its emission growing more compact? Could its spectral lines reveal the nature of the central object? These questions turned G2 into a long-term astrophysical experiment, a live test of survival in one of the most extreme environments in the galaxy. In parallel with these observations, theorists began constructing more detailed models to explain what G2 might be. Simulations of a young star wrapped in an envelope of gas, or the product of a recent binary merger, were run under the gravitational conditions of the galactic center. These models were then compared with the evolving infrared data. The result was a growing convergence between theory and observation. A picture began to emerge of G2 as a new type of transient object, unique not because it was completely unprecedented, but because it was the first time such a thing had been observed so close to a supermassive black hole. This made G2 more than just a curiosity. It became a benchmark, a template against which other mysterious objects in the galactic center could be compared. And indeed, astronomers began to notice that G2 was not alone. Similar infrared bright, dusty, compact sources, collectively referred to as G-objects, had been discovered in the same region. Some of them, like G1, had already passed close to Sagittarius A before G2 did, and had also survived. Others, like G3 through G6, were yet to make their closest approach. Suddenly, G2 was no longer an anomaly. It was part of a family, a class, a population. This realization added even more urgency to the post-Pericenter studies. If G2 was the first clearly documented case of a survivor, what could be learned from the others? Were they also cloaked stars? Merger remnants? Protostars trapped in a gravitational zoo? The persistence of G2 made these questions not just relevant, but essential. It opened the door to a deeper understanding of what kinds of stellar processes were occurring in the very heart of the Milky Way. Moreover, the long-term study of G2 served as a reminder of just how rare and valuable patience is in astronomy. The universe moves slowly. Transformations often unfold over years, decades, or centuries. Yet in G2, astronomers had found a system that evolved in a humanly observable timescale. Watching it meant watching change itself, cosmic change, unfold step by step. And so the follow-up years, rather than diminishing interest in G2, only enhanced it. They turned a narrowly focused event into a long-form narrative, stretching across more than a decade of data and insight. G2 may not have fed the black hole, but it nourished the scientific imagination in a different way. It gave astronomers something few objects ever do, a second act. As the years unfolded after G2's dramatic brush with Sagittarius A, astronomers came to appreciate not just the cloud's resilience, but the remarkable journey it continued to trace through the galactic center, a path both elegant and extreme. G2 wasn't simply a visitor that stumbled into the black hole's vicinity and escaped by chance. It was, and remains, gravitationally bound to Sagittarius A. Its trajectory is a long, sweeping ellipse that plunges deep into the black hole's influence before arcing back out, only to return again in due time. This orbit holds profound clues not just about G2's identity, but about the environment it inhabits and the forces that shape life at the heart of our galaxy. To understand the significance of G2's orbit, we need to grasp just how tight a dance it performs around the galactic center. At its closest approach, known as Pericenter, G2 came within just 260 astronomical units (AU) of Sagittarius A. That's about 40 billion kilometers, a vast distance by earthly standards, but a whisper from destruction in the world of supermassive black holes. For context, Neptune orbits our Sun at a distance of about $30 G2 passed within roughly 9 times that of the outermost planets, orbit from a gravitational abyss more than 4 million times the mass of our Sun. Yet G2 didn't dive straight in. Its orbit was, and still is, highly elliptical. This means it spends most of its time far from the black hole, moving slowly, before swooping in for a brief, intense acceleration near Pericenter. Like a comet in our solar system, it hurtles to its closest point and then escapes back outward, continuing its loop around the galactic center. Orbital tracking conducted using infrared telescopes like Keck and VLT has revealed the parameters of this dramatic arc. G2's orbital period is estimated to be around 300 years, meaning it takes centuries to complete a full lap around Sagittarius A. Its path lies nearly edge-on to our line of sight, allowing astronomers to measure not only its speed and direction, but even the subtle tidal effects that tug at it as it swings past the black hole. But what keeps it in such an orbit? Gravity, of course. But not just the gravity of Sagittarius A. The galactic center is teeming with mass, stars, dark matter, and possibly even clusters of stellar remnants. G2's motion is influenced by all these gravitational contributors. Yet despite these complex forces, the cloud's motion remains remarkably stable and predictable. This stability hints again at an underlying cohesive structure. Something within G2, whether a star or a compact core, provides enough gravitational self-binding to resist being smeared out by perturbations. This orbit is important for another reason: it provides astronomers with a timeline. If G2 completes one loop every 300 years, and we caught it just before and after its pericenter, then we've glimpsed it at a pivotal moment in its long journey. It also means that G2 will return. Centuries from now, future astronomers, or perhaps our descendants, will have the opportunity to observe G2 once again as it plunges towards Sagittarius A for another close encounter. Will it look the same? Will its envelope have dispersed, revealing a naked star? Or will it have evolved into something new entirely? Even now, its ongoing orbit continues to provide valuable data. As it moves away from the black hole, astronomers track how its velocity changes, how its shape evolves, and how its light profile shifts. These observations allow researchers to refine models of gravitational dynamics in the galactic center, testing general relativity in extreme conditions and providing indirect constraints on the mass distribution around Sagittarius A. Interestingly, G2's orbital path also intersects with the orbits of other mysterious objects near the galactic center, such as the so-called S-stars, a group of young, massive stars in tight orbits around the black hole. While G2 does not appear to belong to the same dynamical family, its orbit is a reminder that the inner regions of the galaxy are not static. They are a swirling, ever-shifting ballet of matter and motion. Gas clouds, stars, and potentially stellar remnants all share this extreme environment, governed by the same invisible rules and shaped by the same gravitational hand. The elliptical nature of G2's orbit also reinforces the idea that it may be a relatively recent arrival to its current path. Many astrophysicists believe G2 could have been placed into this orbit following a dynamic interaction, perhaps a gravitational slingshot event, or the aftermath of a binary merger. If that's the case, G2's current orbit may be its first full lap around Sagittarius A, making our observations even more fortuitous. We are, in a very real sense, catching it in the act of adapting to life in one of the universe's most extreme gravitational neighborhoods. And should G2 indeed be a star shrouded in gas or a merger remnant, then its orbit is more than just a celestial track, it's a clock. It tells us how long the gas will remain bound before dissipating, how long the dust will obscure the central source, and how long until this object fully reveals its true nature. Every point along its path brings us closer to answers. In a universe where many events take place on timescales too vast to witness, G2's orbit is a rare opportunity. It allows astronomers to track evolution not in eons, but in years and decades. It connects the present moment to centuries past and future, anchoring our place in the long narrative of galactic history. And as it continues on its arc around the black hole, defiant, intact, and mysterious, it reminds us that even in the shadow of the void, motion endures. Just when astronomers thought G2 might be a unique cosmic oddity, a one-time enigma that had somehow resisted the doom of Sagittarius A, another discovery widened the lens of the mystery. It turned out G2 was not alone. In fact, it was part of a strange and growing family of objects, all lurking within the same treacherous neighborhood near the Milky Way's core. These were the so-called G-objects, a set of peculiar infrared bright entities designated G1, G3, G4, G5, and G6, each sharing similar traits with G2, and each deepening the mystery of what these things really are. The realization that G2 came gradually, as continued monitoring of the galactic center revealed other compact, dusty sources moving on their own orbits around Sagittarius A. The first to catch attention, even before G2 was widely understood, was G1. G1 had actually made its closest approach to the black hole back in 2001, more than a decade before G2's dramatic near-miss, but it didn't draw immediate attention. Only in hindsight did researchers notice something familiar about it. Like G2, G1 survived. It had passed close to the gravitational monster and emerged relatively undisturbed. It too showed infrared emissions consistent with a dusty, ionized envelope, and its orbit was strikingly elliptical, plunging deep toward the galactic center before swinging away. The similarities were impossible to ignore. G1's orbital elements bore a resemblance to G2's, including a similar pericenter distance and a bound elliptical trajectory. Just like G2, G1 did not appear to flare the black hole during its pass, and just like G2, it remained visible and compact in the years following its closest approach. This sparked a question: if two such objects existed, were there more? The answer was yes, and soon, researchers had identified several more candidates: G3, G4, G5, and G6. These were not all discovered simultaneously. Instead, they emerged one by one from deep data analyses, buried in years of infrared observations made possible by adaptive optics and spectroscopic tools at the Keck Observatory and the Very Large Telescope. Each object shared a core set of features: infrared luminosity, extended appearance under high-resolution imaging, compactness in size, and unusual orbital motion that indicated they were gravitationally bound to Sagittarius A. But what exactly were these G objects? At first, theories leaned toward gas clouds, much like the original interpretation of G2. They were small, dusty, ionized, and glowed in the Brachiogamma line, indicating the presence of hydrogen. But that assumption quickly ran into the same problem G2 had posed. If these were only gas clouds, why weren't they destroyed? Why did they persist after their close brushes with the black hole? This led to the emerging consensus that G2 was not unique, but rather the most dramatic example of a broader class of star-like entities hidden in dusty cocoons, objects resilient enough to maintain structure under tidal stress. This class, the G objects, may all be stars in disguise. They could be young stellar objects, still shrouded in the material from which they formed, or merger remnants, products of two stars fusing into one, violently ejecting gas that temporarily hides the core. G3 and G4, for example, exhibit similar emission lines and motion profiles, suggesting they may be at different stages of the same life cycle. They appear slightly less extended than G2, leading some to speculate that they might be older, with less surrounding dust, or perhaps younger and not yet fully bloomed. G5 and G6 are even more mysterious, fainter, less studied, but exhibiting comparable characteristics that tie them to this ghostly fraternity. One theory gaining traction proposes that these G objects may be products of binary star systems, common in the dense stellar environment near Sagittarius A. Over time, these binaries can merge due to gravitational interactions, creating bloated stars surrounded by hot, thick envelopes of gas and dust. These envelopes are what we observe as the glowing, diffuse halos of the G objects. The merger scenario would also help explain why these objects survive close approaches. They're not fragile clouds, but massive stars wearing veils of their own past chaos. Another hypothesis suggests they might be young stars formed relatively recently in the hostile galactic center. This region, contrary to earlier assumptions, may still host pockets of star formation. In such an environment, new stars could emerge still wrapped in their dusty birth material, appearing cloud-like in infrared observations but ultimately revealing themselves as compact, dense stellar bodies over time. And then there's the intriguing possibility that the G objects are all part of a particular population, perhaps the product of a past starburst or dynamical interaction that seeded these unique entities into their current orbits. If that's the case, the galactic center may contain far more G-type objects than we currently detect. Many may remain hidden behind dust, or too faint to resolve with current instruments. G2, then, was merely the brightest flare in a forest of subtle glows. Their orbits, too, add another layer of intrigue. While they are not all identical, many of the G objects trace elliptical paths that bring them startlingly close to Sagittarius A before pulling away. This recurring theme reinforces the idea that these objects are robust, able to navigate the tidal hell of the black hole's near field without being stripped apart. Their trajectories also suggest they've been orbiting the black hole for significant lengths of time. Some may have completed several full orbits. Others could still be on their maiden plunge. In the context of the broader galactic environment, the discovery of this G object family revolutionizes our understanding of what survives near a supermassive black hole. It challenges the idea that the region is a lifeless void, ruled only by destruction. Instead, it suggests a dynamic ecosystem, one where stars are born, collide, merge, evolve, and sometimes cloak themselves in mystery, orbiting in a gravitational ballet beneath a curtain of dust. These objects have become a new class of observational targets. Scientists now comb through archived data with fresh eyes, hunting for signs of other G-like phenomena. As instruments improve and next-generation observatories like the James Webb Space Telescope continue to scan the galactic center, we may soon find more of these ghostly travelers, and perhaps even learn their life stories in full. For now, the G objects remain tantalizing cosmic riddles, embers glowing in the dark, too dense to disperse, too faint to fully resolve, and too numerous to ignore. The more astronomers observe the G objects near the galactic center, G1 through G6 and perhaps even others still hiding in the shadows, the more one central question began to rise above the rest. What if they're not gas clouds at all? What if every single one of these strange, infrared bright blobs is actually a star, veiled by its own ejected material, masquerading as something fragile and ghostly? Could it be that we're looking at an entire class of stellar objects, not scattered anomalies? This idea that the G objects might represent a new class of celestial body is not only intriguing, it's potentially paradigm-shifting. Stars with dusty envelopes are not a new concept in astrophysics. In fact, they are fairly common in other parts of the galaxy. But seeing them in such an extreme environment, right in the jaws of a supermassive black hole, raises a whole set of questions about their origins, evolution, and survival mechanisms. Let's start with the idea of a dusty envelope. When a star either forms, evolves, or undergoes a major disruption like a merger, it often becomes surrounded by gas and dust. This surrounding material can block visible light, while emitting strongly in the infrared, making the object appear fuzzy or cloud-like when observed with infrared telescopes. If the envelope is thick enough, it can completely obscure the star's light, creating the illusion of a diffuse gas cloud with no solid core. But as we've seen in the case of G2, and increasingly with G1, G3, and others, these clouds do not behave like ordinary interstellar gas. They resist tidal disruption. They maintain coherence. They orbit Sagittarius A with paths that resemble those of bound stars. They glow steadily for years, even decades. All signs point to something more massive and compact hiding within the mist. If all the G objects are indeed stars cloaked in dusty envelopes, it would solve many of the observational puzzles at once. Their survivability near the black hole suddenly makes sense. The gravity of the central star helps hold the envelope together, resisting the tidal forces of Sagittarius A. Their infrared emissions are no longer puzzling either, just the thermal signature of warm dust heated by starlight or leftover energy from a recent stellar event. Their orbits, while eccentric, are consistent with objects that have mass and internal cohesion. But if these are cloaked stars, then where did they come from? One theory posits that they are the products of stellar mergers. In the dense stellar environment around Sagittarius A, gravitational interactions are common. Stars can form close pairs, binary systems, that spiral into one another under the influence of nearby masses or through energy loss via gravitational radiation. When they merge, the result can be a single, puffed-up object that ejects a shell of gas and dust in the process. This new star, temporarily shrouded in its own expelled matter, would look very much like what we see in the G objects. Another possibility is that some of these stars were born in place. The galactic center isn't just a graveyard of matter, it may also be a cradle. Despite the chaotic tidal forces and intense radiation, there is evidence of recent star formation in this region. Some of the most massive and luminous stars in the Milky Way are found surprisingly close to Sagittarius A. Perhaps the G objects represent a special phase in the life cycle of stars formed near the galactic core, a phase where they are still wrapped in their natal clouds, slowly shedding the material as they mature. Still another hypothesis is that the dusty envelopes are maintained not by birth or collision, but by ongoing processes. For example, strong stellar winds could eject material continuously, forming a thick shell around the star over time. In this model, the G objects would be more akin to massive, evolved stars in a stage similar to Wolf-Rayet stars, hot, luminous stars that lose mass at a rapid pace, forming thick clouds of outflowing gas and dust. If this is the case, then we're looking at stars that are not just surviving near the black hole, they're thriving, actively reshaping their surroundings. Regardless of their origin, the implications of a whole class of dusty envelope stars near the galactic center are profound. For one, it means that the galactic core is far more complex than previously thought. It's not a simple void with a black hole at the center and a few tightly bound stars orbiting around it. It's a dynamic, multi-layered ecosystem filled with stars at different evolutionary stages, many of them hidden beneath cloaks of dust and gas. This also challenges our assumptions about stellar evolution in extreme environments. If stars can survive, and even form, within just a few hundred astronomical units of a supermassive black hole, then the boundary of where stars can exist is far more flexible than imagined. The G objects teach us that tidal forces, while powerful, are not the final word. Structure, mass, and cohesion can triumph even in the most dangerous corners of the galaxy. Perhaps most intriguingly, if these objects are all part of a common class, then there must be many more of them. Some may be too faint to detect with current technology. Others may be orbiting farther out, or on trajectories that never bring them into observational range. But as infrared instruments grow more sensitive, and as future missions like the Extremely Large Telescope and the James Webb Space Telescope continue their scrutiny of the galactic center, we may find that the G-class population is just the tip of a much larger iceberg. G2, once thought to be an oddball, now appears to be a member of an entire stellar tribe. And that realization, that the universe has repeated this strange formula not once, but many times, changes everything. What was once a curiosity is now a phenomenon. A class. A mystery multiplied by 6, and counting. Peering into the heart of the Milky Way is no simple task. The galactic center lies shrouded behind colossal curtains of interstellar dust and gas, so thick and opaque that visible light is almost entirely blocked. From Earth, it's as if the center of our galaxy is veiled in permanent night. For centuries, it remained hidden, a blind spot in our understanding of the cosmos. But everything changed with the advent of infrared astronomy. And it was this very capability, this ability to see through the dark, that made tracking G2 and its family of mysterious companions possible in the first place. Infrared light, with its longer wavelengths, behaves very differently from visible light. While optical light scatters off small dust particles and becomes absorbed by thick clouds, infrared radiation can slip between those particles, threading through the obscuring material like a beam of light through fog. This makes it the perfect tool for observing environments like the galactic center, where the chaos of star formation, black hole activity, and dense interstellar matter would otherwise be impossible to study directly. The instruments that made G2's story possible are among the most advanced ever built. Chief among them were the Keck Observatory in Hawaii and the European Southern Observatory's Very Large Telescope, VLT, in Chile. These observatories are equipped with state-of-the-art adaptive optics systems, which correct for the blurring effects of Earth's atmosphere in real time, sharpening infrared images to an unprecedented degree of clarity. When astronomers first detected G2 in 2011, it was through infrared imaging of the galactic center taken with these telescopes. The cloud appeared as a faint reddish glow, a tiny, compact smudge in the midst of the crowded and turbulent region near Sagittarius A. Without the ability to capture infrared light, it would have gone completely unnoticed. But through these observations, astronomers were able to not only spot G2, but begin mapping its trajectory through space. The infrared signature of G2 came primarily from emission lines of hydrogen, specifically the bracket gamma line. This line, located in the infrared part of the spectrum, forms when electrons in hydrogen atoms drop from higher energy levels to lower ones. In the case of G2, this emission was likely caused by ionization, where nearby ultraviolet radiation from hot stars stripped electrons off hydrogen atoms, and those electrons later recombined. The result was a telltale glow, clear and distinct in the infrared spectrum, that allowed G2 to be tracked like a cosmic beacon. Spectroscopy, a powerful tool that dissects light into its component wavelengths, played a crucial role as well. With infrared spectrometers mounted on Keck and the VLT, scientists could measure not only the brightness of G2's emission but its Doppler shift, how the light was stretched or compressed as the cloud moved toward or away from us. This provided incredibly detailed velocity data, allowing astronomers to trace G2's path with precision. They could see it accelerate as it fell towards Sagittarius A, slow as it rounded Pericenter, and then drift outward again on its bound orbit. In many ways, infrared astronomy transformed G2 from a blurry unknown into a character with a story, a plotline written in heat, motion, and gravity. Through each new observation campaign, telescopes captured snapshots of its evolution, the subtle stretching of its shape, the fluctuations in brightness, the twist in its tail as it passed closest to the black hole. These observations, impossible in visible light, became chapters in an unfolding cosmic drama. And the role of infrared telescopes didn't stop at detection and tracking. They were also instrumental in revealing what G2 was not. For example, if G2 had been a pure gas cloud with no internal structure, its signature would have changed drastically after Pericenter, brightening as it was torn apart and feeding the black hole. But the relative stability of its infrared emission hinted at something more robust inside, a clue that eventually led scientists to hypothesize the presence of a hidden star or merger remnant. Additionally, continued IR monitoring helped differentiate G2 from the background chaos of the galactic center. This is not a quiet region, it's packed with stars, flares, shocks, and streams of gas. Yet thanks to precise IR observations over years, astronomers could isolate G2's motion and behavior, ensuring that they were not confusing it with other phenomena. It became not just a discovery, but a confirmed, persistent object worthy of detailed study. In recent years, even more powerful infrared tools have come online. The gravity instrument on the VLT interferometer, for instance, allows for incredibly high-precision measurements of motion and light at the very core of the galaxy. Gravity's contributions have refined our understanding of G2's orbit and allowed astronomers to measure the gravitational effects of Sagittarius A with astonishing detail, further confirming the black hole's mass and position, and testing general relativity in one of the most extreme environments available. The James Webb Space Telescope, JWST, although not yet primarily tasked with monitoring the galactic center, also holds immense promise for the future of geobject studies. With its ultra-sensitive infrared instruments and location in space, free from Earth's atmospheric interference, JWST could detect fainter, more distant, or more deeply obscure G-type objects that ground-based telescopes might miss. If G2 is one of many, as current evidence suggests, then JWST may help us uncover the full population, revealing just how common cloaked stars are near black holes. Ultimately, the tale of G2 would have been impossible without the eyes that see in the dark. Infrared astronomy didn't just reveal the object, it revealed an entirely new class of cosmic behavior, hidden in a region long thought too chaotic and obscured to study. It showed us that even in the places we can't see with our own eyes, the universe is active, dynamic, and filled with stories waiting to be told. Through the lens of infrared telescopes, the galaxy's core, once a dark and silent void, became a place of revelation. G2 was merely the first spotlighted act. And there are surely more waiting in the wings. Gravity, the silent architect of the cosmos, played an orchestral role in the saga of G2. From the moment it was discovered, to the instant it brushed dangerously close to the event horizon of the supermassive black hole at the heart of our galaxy, G2 was dancing under gravity's command, a dance that revealed not just the fate of the cloud, but also the secret rhythms of the galactic center itself. To understand how gravity sculpted G2's story, we must begin with the fundamental truth of our universe. Gravity dominates on large scales. Every trajectory, every orbit, every compression or elongation of a celestial body begins and ends with gravity. And in the galactic center, gravity takes on an especially fearsome character. It becomes steep, deep, and unforgiving, warping space and time around Sagittarius A with such intensity that even light must bend to its pull. G2's approach toward the black hole was entirely governed by this curvature of spacetime. From the moment it was set on its orbit, possibly eons ago, it was destined to loop ever closer to this invisible force. Its path, a highly elliptical orbit, shows us gravity in its dynamic form. Near apocenter, the farthest point of its orbit, G2 drifted slowly through space, bound but seemingly unhurried. But as it fell inward, gravity pulled harder, accelerating G2 to staggering speeds as it neared Pericenter. This acceleration wasn't just theoretical. Observations of G2 showed it speeding up dramatically as it descended toward the black hole. By the time it reached its closest point, just $260 from Sagittarius A, it was moving at thousands of kilometers per second. This is the raw kinetic energy that gravity imparts, a signature of the gravitational gradient that dominates the galactic center. The black hole was not simply attracting G2, it was flinging it around a cosmic curve at immense velocity. But gravity did not only control the motion of G2, it also molded its shape. One of the most striking effects of gravity, particularly near black holes, is the phenomenon of tidal forces. Unlike the uniform gravitational pull we experience here on Earth, tidal forces arise when one side of an object feels a significantly stronger gravitational pull than the other side. In the case of G2, as it approached the black hole, the leading edge of the cloud felt a stronger pull than the trailing edge. The result was a stretching, an elongation of the cloud along its axis of motion. This stretching was visible in real time. Astronomers noted that G2 became more elongated and filament-like as it neared Sagittarius A, forming a kind of tail, much like a comet in the solar system does when influenced by the sun's radiation and gravity. But in this case, the sculptor wasn't solar wind or heat, it was pure gravitational strain. This process, often referred to as spaghettification, when it occurs near black holes, was expected to go further. Many astrophysicists predicted that G2 would not survive its encounter, believing that the tidal forces would shred it completely, dispersing its material and feeding it to the black hole. In fact, models predicted a dramatic flare-up of Sagittarius A as it consumed the gas, lighting up in X-rays and infrared like a cosmic beacon. Yet that didn't happen. Why? Because gravity doesn't act in a vacuum. Its effects depend on the structure and cohesion of the object it's acting upon. And G2, as it turned out, was more than just a diffuse, formless cloud. It had internal integrity, likely a dense central core, perhaps a star or a stellar remnant, bound tightly enough to resist the full brunt of the tidal forces. In other words, gravity tried to rip it apart, but another force, G2's own self-gravity, fought back. This internal gravitational cohesion is one of the key reasons G2 survived. While the outer envelope of dust and gas was deformed, possibly even partially stripped, the core held. And this tells us something profound not just about G2, but about the environment it exists in. The galactic center is not simply a place where matter goes to die. It is a place of gravitational negotiations, where mass, velocity, density, and orbital dynamics all converge to create outcomes far more complex than simple consumption. It also tells us about the gravitational structure of the central parsec of our galaxy. G2's orbit, tracked meticulously before and after Pericenter, has provided scientists with one of the best gravitational maps of the region. By watching how G2 responded to the gravitational field, researchers were able to refine estimates of the mass of Sagittarius A, the distribution of other masses nearby, and even test Einstein's general relativity in an extreme environment. In fact, small deviations in G2's trajectory have been used to look for the influence of nearby stars, dark matter clumps, or stellar remnants like black holes and neutron stars. Its behavior is a probe, a tiny, glowing sensor responding to every gravitational wrinkle in the galactic center. And so far, it has confirmed that Sagittarius A behaves exactly as a supermassive black hole should, while also revealing a crowded, dynamic region filled with hidden mass and complex interactions. G2's continued journey, shaped by gravity but not consumed by it, paints a picture of resilience and precision. It shows us that even in the most dangerous places in the universe, not all matter is doomed. Gravity is not merely a destroyer, it is also an artist, a guide, and a narrator of cosmic histories. And as G2 continues along its elliptical path, it remains under gravity's watchful influence. Every future loop will be dictated by its mass and momentum, by the gravitational tugs of nearby stars, and by the silent pull of Sagittarius A. It is caught, permanently, in a gravitational waltz with the dark heart of the galaxy. A waltz we are now privileged to watch, one observation at a time. G2's extraordinary journey did more than defy expectations. It peeled back a layer of mystery from one of the universe's most elusive forces, the behavior of supermassive black holes. For decades, astronomers have puzzled over the dual personality of black holes. At times, they flare violently, devouring matter and radiating intense light across the electromagnetic spectrum. At others, they remain eerily silent, as though dormant, ignoring the matter drifting nearby. G2's close pass around Sagittarius A didn't just raise questions about the cloud's survival. It forced scientists to reevaluate what we thought we knew about how black holes feed, flare, and fall silent. Before G2, the prevailing expectation was that a gas cloud approaching a supermassive black hole at such a close distance, just a few hundred astronomical units, would ignite a dramatic event. The gravitational tides of Sagittarius A would tear it apart, funneling its material toward the event horizon in a cascade of heated accretion. This influx of matter would be expected to trigger a flare, possibly in X-rays or infrared, as friction and compression heated the gas to millions of degrees. Flares from other galaxies, quasars, active galactic nuclei, had shown us what such feeding frenzies could look like. G2, falling toward our own black hole, was thought to be the perfect test case to catch one in the act. But that flare never came. In the lead-up to G2's Pericenter in 2014, telescopes around the world, including the Chandra X-ray Observatory, SWIFT, the Very Large Telescope, and the Keck Observatory, were pointed at Sagittarius A. Astronomers were poised for a fireworks display, expecting a dramatic surge in brightness. They monitored it for months, capturing a steady stream of data in various wavelengths. Yet Sagittarius A remained stubbornly quiet. No sudden outburst, no massive spike in X-rays, no telltale burst of radio waves. The anticipated feeding event simply didn't happen. This quietness forced the scientific community to confront an uncomfortable but enlightening truth. Supermassive black holes are far pickier eaters than we once believed. G2 taught us that not all matter crossing close to the event horizon is automatically swallowed. Black holes are not vacuum cleaners. They do not indiscriminately consume everything in their vicinity. Accretion, the process by which matter falls into a black hole, is far more complex than just gravitational pull. There are pressure gradients, magnetic fields, angular momentum barriers, and competing flows of stellar wind, all of which can prevent material from reaching the final, fatal plunge. In G2's case, several factors may have combined to prevent accretion. First, its material was likely too diffuse. The outer gas and dust may have lacked the density necessary to overcome internal turbulence and gravitational counterforces. Second, the material may have had too much angular momentum, spinning around Sagittarius A rather than falling directly into it. Third, the black hole's own environment may have included existing winds or radiation pressure that actively pushed the cloud's gas away before it could settle into the accretion disk. What this means is that the quietness of Sagittarius A is not just a result of a lack of material nearby. It's also about how that material behaves when it gets close. The process of accretion appears to be gated and inefficient. It's possible for clouds of gas to pass near the black hole and emerge intact or partially scattered, without ever triggering the dramatic consumption we associate with active galactic nuclei. This helps explain why our own galaxy's black hole is so faint compared to its cousins in other galaxies. Sagittarius A is over 4 million times the mass of our Sun, but it radiates barely more than our Sun in many bands of light. In the cosmic sense, it's starved. But now we know that even when a meal arrives, it may not be eaten. The case of G2 also refined our understanding of how black holes transition between quiet and active phases. In the broader universe, some black holes suddenly flare up after centuries of silence. These flares could be triggered by much denser or better aligned clouds than G2, or by stars that wander too close and are torn apart in tidal disruption events. G2 shows us the borderline, what happens when the conditions for flaring are almost met, but not quite. It is a glimpse into the threshold of activity, into the conditions that must align before a black hole stirs from its slumber. Additionally, G2's passage allowed astronomers to test their accretion models in real time. Simulations had predicted spikes in light, increases in X-ray flux, or even subtle shifts in radio emissions. When these predictions failed to materialize, it offered valuable calibration. The models were adjusted. New parameters were added. The understanding of viscosity in the accretion disk, the role of magnetic fields, and the stability of the inner flow zone, all were reassessed in light of G2's silent transit. The observations also served to reinforce the idea of quiescent black holes, supermassive entities like Sagittarius A that can exist in a low luminosity state for eons. While other black holes blaze in distant galaxies, ours glows dimly, occasionally flickering with modest activity, but mostly quiet. G2 didn't awaken the giant. It merely brushed against it. Yet, even in its silence, Sagittarius A was speaking. Through G2, it whispered of thresholds and subtleties, of how not all matter makes it to the final embrace. It taught us that flaring is not inevitable, and that understanding accretion requires not just catching black holes in their active states, but observing them in their restraint. So, what did G2 teach us about black holes? It taught us humility. That even the most anticipated cosmic events may defy prediction. That the mechanics of feeding are intricate and conditional. That accretion is not a given, but a finely tuned orchestration. It reminded us that supermassive black holes, often painted as cosmic gluttons, may instead be cautious connoisseurs, consuming only what meets the precise requirements of their invisible engines. In G2's passage, the black hole revealed something precious. Its capacity for stillness, its resistance to impulse, and its role not just as a destroyer, but as a gatekeeper of the galactic core. For decades, the image of a black hole has been painted with awe-inspiring finality, a cosmic vacuum cleaner with an insatiable appetite, sucking in everything that crosses a certain point of no return. Popular science, media, and even some earlier astrophysical models help cultivate the myth that matter approaching a black hole, especially a supermassive one like Sagittarius A, has no chance of escape. Once you fall in, you're gone. Even getting close meant near certain doom. But the G2 cloud's encounter with Sagittarius A didn't just challenge that myth. It cracked it wide open and revealed an entirely different kind of cosmic reality. Before G2, the general consensus was relatively straightforward. A gas cloud falling toward a black hole would experience extreme tidal forces, be shredded into filaments, and form streams of infalling material. As this matter spiraled inward, it would heat up due to compression and friction, producing intense flares of electromagnetic radiation, particularly X-rays and infrared light. The closer the material got, the faster it would move, and the hotter it would become, eventually adding to the accretion disk or plunging directly into the event horizon. It was neat. Predictable. Devour, flare, fade. Then came G2. It approached dangerously close, just 260 astronomical units from the black hole, well within a range where gravitational shredding was thought to be inevitable. And yet, the cloud remained intact. Not just for a moment, but for years. Its envelope was elongated and distorted, yes, but not annihilated. Sagittarius A did not flare dramatically, did not light up with the expected energy surge. G2 sailed past, wounded perhaps, but not consumed. This was not a minor deviation. It was a revelation. It showed that the path to accretion is not as straightforward as once believed. The notion that everything gets swallowed was too simplistic. G2 proved that there are boundaries, exceptions, thresholds that matter must cross before it can truly be claimed by a black hole. And that changed everything. One of the main reasons G2 wasn't devoured lies in the nature of accretion itself. Accretion isn't merely a gravitational process, it's a finely balanced dance of physics. Matter must lose energy and angular momentum to spiral inward. In many cases, matter arriving near a black hole has significant angular momentum, forcing it into elongated orbits that keep it from falling straight in. It can circle for years, even millennia, never quite reaching the inner regions unless acted upon by external forces, magnetic fields, turbulence, or interactions with other matter. In G2's case, its gas was too diffuse and too fast-moving to easily settle into an accretion disk. Without a braking mechanism to shed angular momentum, it couldn't fall inward effectively. Instead, its material likely continued on its orbital path, slowly dispersing, with only tiny fractions, if any, managing to lose enough energy to make their way toward the black hole's event horizon. Additionally, there may have been environmental factors at play. The area around Sagittarius A is not empty, it's populated by hot gas, stellar winds, and magnetic fields. These can interact with incoming material, stripping, heating, or even deflecting it. The black hole may be surrounded by a buffer zone, a sort of gravitational moat that filters what comes close. G2 may have been caught in these complex currents, partially absorbed but never fully captured. What makes this especially important is how it shifts our understanding of black hole feeding cycles. For years, astronomers looked at other galaxies where central black holes flare dramatically, assuming that those events represented the standard behavior. G2 reminded us that quiescence is not failure to feed, it may be the norm. Black holes might spend the majority of their existence in states of low activity, punctuated only occasionally by true feasting events. This reframes how we interpret galactic centers across the cosmos. If even a cloud as seemingly vulnerable as G2 can survive a close encounter, then many other interactions may go unnoticed or misunderstood. Not every approaching object results in a flare. Not every infall leads to accretion. Some matter dances along the edge, teetering on the cusp, but never quite falling in. The myth of inevitable accretion also obscures the delicate role that black holes play in galactic ecosystems. If Sagittarius A devoured every piece of matter that wandered too close, it would grow rapidly and release constant, destabilizing energy into the surrounding environment. But G2 shows that the system is more balanced. The black hole is selective. The rate of accretion is modulated. The black hole's influence extends far beyond the event horizon, but that influence is nuanced, not absolute. Furthermore, this event has implications for models of early galaxy formation. Supermassive black holes formed in the early universe, yet we still struggle to understand how they grew so large so quickly. Did they consume massive quantities of gas in early feeding frenzies? Or did they grow gradually, through sporadic, inefficient accretion over billions of years? G2's survival supports the latter model. It suggests that unless conditions are ideal, even available matter may not contribute significantly to a black hole's mass. In essence, G2 is a case study in cosmic restraint. It reveals that supermassive black holes are not eternally insatiable. They are governed by complex physics that sometimes prevent them from feeding at all. This turns them from monsters into managers, selective participants in galactic dynamics, rather than chaotic destroyers. The accretion myth, one of instant consumption, may still apply in extreme scenarios, such as a star wandering too close and undergoing tidal disruption. But G2 forces us to broaden our perspective. Accretion is a process, not an inevitability. And sometimes, even in the most extreme gravitational fields, matter finds a way to escape its fate. From the moment G2 was first spotted hurtling toward Sagittarius A, it appeared to be a fragile wisp of gas, an ephemeral blot of dust, and ionized hydrogen lit faintly in the infrared. Its elongated shape, its nebulous boundaries, and its soft spectral glow all screamed vulnerability. To astronomers, it looked like a textbook case of a doomed gas cloud on a one-way trip toward tidal annihilation. But as time passed, and G2 refused to be shredded, devoured, or even meaningfully disrupted, a new and provocative idea began to surface. What if G2 wasn't what it seemed? What if this so-called cloud was wearing a disguise, a faint veil over something far sturdier, far more permanent? This hypothesis emerged not from speculation, but from necessity. The cloud's resilience in the face of the black hole's tidal forces simply didn't match the predictions. Models of pure gas clouds showed that such entities should stretch, fragment, and disperse as they neared a supermassive black hole. The gravitational differential across even a small cloud, only $100 across, for example, would be extreme. The closer side would be pulled much more strongly than the far side, resulting in spaghettification and a stream of material being siphoned off, leading to a spectacular flare as the material entered the accretion zone. But this didn't happen with G2. Instead, G2 emerged from its encounter merely stretched, with its central glow intact and its motion largely unchanged. This anomaly forced astronomers to re-examine the core assumptions. Perhaps G2 wasn't a simple cloud after all. Perhaps it was more like a cloaked object, something solid or compact surrounded by a dusty envelope, and thus misidentified in its early observations. In other words, G2 may have been a case of stellar disguise. The leading theory suggested that G2 harbored a star at its center, a small, young star or a compact stellar remnant, enshrouded in a cocoon of gas and dust. From a distance, this envelope would dominate the observed emission, making the object look like a faint cloud. But under that gauzy veil, there could be a core object held together by gravity, dense enough to resist tidal forces that would rip a simple gas cloud to shreds. Evidence for this hypothesis began accumulating after G2's Pericenter passage. Despite predictions of total disruption, the cloud retained a concentrated central region. This compactness strongly suggested the presence of a gravitational anchor, something that not only held the envelope together during the violent encounter, but also continued to shepherd its trajectory afterward. The motion of the object, too, remained surprisingly coherent. Instead of scattering in all directions, G2 kept moving along a highly elliptical orbit, as if its center of mass had never wavered. Even the stretching and tidal distortion seen in G2 before Pericenter now took on a different meaning. If G2 had a dense star at its center, then the outer gas and dust would be susceptible to tidal stripping, but the star itself would remain intact. This would explain the elongation seen in the cloud, coupled with its post-passage survival. The outer layers may have been peeled off or scattered slightly, but the central object endured, quietly hidden beneath the chaos. Some astronomers even compared this behavior to that of certain stars in the Orion Nebula and other stellar nurseries, where young stars are born wrapped in thick cocoons of gas and dust. These protostars often exhibit extended infrared emission, similar to G2, and can masquerade as diffuse clouds when observed with limited resolution. The analogy was compelling. Perhaps G2 wasn't just a lost cloud, it was a cloaked stellar traveler, moving through one of the most extreme environments in the galaxy. This idea also helped reconcile G2 with the behavior of its siblings, the so-called G objects. Several of these, including G1 and G3, had similarly ambiguous appearances, cloud-like but stable over time. Each followed a distinct orbit through the central parsec, and several showed signs of compactness and resilience. If G2 had a star within, perhaps all the G objects were part of a hidden stellar population, each masked by thick circumstellar envelopes. Of course, this didn't mean G2 wasn't a cloud at all. It still had a gaseous component, evident in its infrared emission and spectral features. But what had once seemed like its entire identity, the fragile glow of a drifting cloud, was now just the outer layer of a more complex being. Beneath the veils of dust and ionized hydrogen might lie a product of stellar evolution, a young star, or even the remnant of a recent merger. This interpretation elevated G2 from a curiosity to a key player in understanding the galactic center. If stars could exist shrouded in dense envelopes so near to Sagittarius A, it implied that star formation or stellar collisions might be more common in the region than previously thought. It also suggested that our methods of classifying objects near the black hole needed refining, that we might be undercounting compact sources hidden by dust and misclassifying some of the most dynamic objects in our galaxy. And perhaps most importantly, the disguise reminded us how deceptive appearances can be in astronomy. The universe doesn't always show its cards face up. Objects that seem fragile may hide strength. Structures that appear doomed may hold secrets. In the case of G2, a faint cloud drifting toward destruction turned out to be a survivor, and perhaps, a wanderer wrapped in stellar armor. The case of G2, and its possible siblings in the G-object family, has profound implications far beyond the scope of a single gas cloud's survival. It has opened a new window into one of the most elusive and turbulent environments in the universe, the galactic core. At the heart of the Milky Way, where stars swirl tightly around a supermassive black hole and where gravitational chaos reigns, the discovery of compact, dust-enshrouded objects like G2 invites an urgent question. Are we witnessing a new, hidden chapter in the story of star formation and evolution? Traditionally, the galactic center was thought to be too hostile for the fragile process of star birth. The immense gravitational forces from Sagittarius A, the high radiation fields, strong magnetic activity, and the constant bombardment of stellar winds create an environment where molecular clouds, those cool, dense cradles of new stars, should be shredded before they can collapse and form anything coherent. This assumption led to a long-standing paradox. If star formation is so improbable in this region, then why do we find so many young, massive stars orbiting just light days from the central black hole? Enter G2. If G2 is indeed a cloak star, possibly formed via a stellar merger or born within a shrouded cocoon of dust and gas, it provides one of the clearest signs yet that star formation, or at least stellar transformation, can and does happen in this extreme regime. And not just once. The identification of multiple similar objects, G1 through G6, suggests this is not a one-off event. It hints at a recurring mechanism or environment that fosters such entities. These may be newborn stars wrapped in embryonic material, or merger remnants glowing in the aftermath of a violent coalescence. Either way, they defy old assumptions and point to active stellar processes right in the heart of the Milky Way. One of the most intriguing possibilities is that G2 is the aftermath of a stellar merger, a scenario where two stars, possibly a binary system, spiral into one another due to gravitational interactions or external perturbations. In the crowded stellar nurseries near the galactic core, such encounters are likely far more common than in the calm suburbs of the galaxy. Stars on eccentric orbits can pass perilously close to each other. Tidal forces, three-body interactions, or even the gravitational influence of Sagittarius A can disrupt their delicate dance. If two stars collide or coalesce, the result is a single, rejuvenated object wrapped in a thick veil of gas and dust thrown off during the merger. This idea is not speculative. In recent years, astronomers have identified similar merger candidates elsewhere in the galaxy, such as V1309 Scorpii, a stellar collision observed in real time in 2008. The star brightened dramatically before fading, and later observations showed an expanding envelope of gas and dust, eerily reminiscent of G2's characteristics. If such mergers are common near Sagittarius A, then we may be looking at a whole population of stars that were not born recently but rather reborn through collision and union. This revelation carries deep implications for how we interpret stellar populations and galactic cores. It may explain the surprising youth of some stars near Sagittarius A, objects that should not have formed in such a hostile place. Perhaps they didn't form there at all, but rather migrated inward or were rejuvenated through mergers. The G objects could be the visible remnants of such events, still cooling, still glowing through their dusty veils. Moreover, these merger events might play a key role in seeding further star formation. The chaotic environment around the black hole can compress gas clouds as they are tidally squeezed and sheared. If these clouds are dense enough, the compression might trigger collapse, starting the star formation process in spite of the hostile surroundings. It's a galactic paradox. The same forces that seem to inhibit birth might also catalyze it under the right conditions. The observational tools that allowed us to see G2 are also pivotal in this new understanding. Infrared astronomy. particularly with instruments like the Very Large Telescope's Symphony and Keck's NIRC-2, allows astronomers to peer through the thick veil of interstellar dust that obscures the galactic center. Without infrared observations, G2 would have remained invisible, one more anonymous smudge in the dark. But with these tools, we can now identify and track dusty, compact objects in real time, observing their motion, morphology, and spectral properties as they orbit the black hole. And as we do, more questions emerge. Are these G objects truly stars in disguise, or are some still forming? Do they represent the tip of the iceberg, a visible sign of a vast, hidden population of cloaked stellar remnants or embryos? Could some of them evolve into massive stars, or will they be shredded in time by the same tidal forces they so narrowly escaped? The implications extend beyond the Milky Way. If star formation and stellar mergers can occur even in our galaxy's violent core, then similar processes might be happening in the centers of other galaxies as well, especially those with actively feeding black holes or densely packed nuclear star clusters. These regions, once dismissed as star formation dead zones, might instead be cradles of exotic stellar evolution, shaped by the very forces once thought to prevent it. In the end, G2 may not have just survived the black hole. It may have illuminated the hidden life cycles of stars in the most extreme environments. It has become a kind of cosmic messenger, whispering that the galactic core is not only a realm of endings, but also of transformations, rebirths, and perhaps, unlikely beginnings. If G2 is more than just a drifting gas cloud, if it is in fact a cloaked stellar body, then the dusty envelope that first made it visible to us might not be some random bit of galactic debris. Instead, it may be a direct product of the star itself, cast off through powerful and continuous stellar winds. In this view, G2's glowing veil of gas and dust is not merely a passive shroud but an active emission, constantly replenished, sculpted, and energized by its hidden core. Stellar winds are an essential and often underestimated force in astrophysics. They are streams of particles, primarily protons, electrons, and ions, ejected from the surface or outer layers of a star. Depending on the star's type and age, these winds can range from gentle breezes to violent gales traveling at hundreds, or even thousands of kilometers per second. Over time, these winds can carry away significant amounts of mass, forming diffuse halos or dense clouds around their host stars. In the case of G2, this process may explain the very structure that allowed us to detect it. The infrared glow picked up by telescopes such as VLT and Keck wasn't coming from a luminous star directly. It was the thermal emission of dust grains warmed by starlight, interspersed with ionized gas excited by ultraviolet radiation. These materials are classic hallmarks of stellar wind activity, particularly in young or recently merged stars where turbulent atmospheres drive vigorous mass loss. Imagine a small, compact star nestled deep in the galactic center, constantly shedding layers of itself into the surrounding space. Over years or decades, this process builds up a dense envelope, rich in dust and gas. As the star orbits closer to Sagittarius A, tidal forces may begin to strip away some of that envelope, stretching and heating it, but not destroying the star at the center. The material we saw moving, distorting, and glowing was not the star's true self, but the outer shell it casts off, its stellar wind caught in the act of being reshaped by the galaxy's most powerful force. This model elegantly explains several of G2's most puzzling characteristics. First, its persistence. A normal gas cloud with no internal source would eventually disperse, especially after a close pass by a supermassive black hole. But if the cloud is continuously replenished, if the central star keeps blowing out new material, then it could maintain a roughly stable appearance for many years. This would also explain why G2's brightness didn't vanish after Pericenter. The dusty envelope wasn't entirely consumed because new material kept flowing outward. Second, the shape and motion of the cloud make more sense in this context. A pure gas cloud would deform rapidly under tidal forces, breaking into filaments or streams. But G2's central concentration remained surprisingly intact, indicating that something, likely the star's gravity, was binding the surrounding gas. A wind-driven envelope naturally has a density gradient, thickest near the source and thinning outward. When such a structure encounters tidal stretching, the outer layers may trail behind, while the inner ones remain tightly bound to their origin. This is exactly what astronomers saw. Third, the emissions from G2 fit this hypothesis. The hydrogen recombination lines observed, especially in the infrared, are consistent with ionized winds, not passive interstellar clouds. These lines arise when electrons recombine with protons to form neutral hydrogen, releasing energy in the process. In wind-driven envelopes, ionization can occur from both the star's own radiation and from shocks generated as the wind interacts with surrounding material or external forces, such as those from Sagittarius A. There's even precedent for such structures elsewhere in the galaxy. Consider the famous Wolf-Rayet stars, massive stars in the late stages of their lives, shedding their outer layers through intense winds. These stars are often surrounded by dense, glowing shells of ejected material, sometimes forming complex structures like rings, arcs, or expanding bubbles. While G2 is far less massive than a typical Wolf-Rayet star, the underlying physics of wind envelope formation is similar. The key difference lies in the environment. Where Wolf-Rayet winds blow into the relatively calm interstellar medium, G2's wind is doing battle with the gravitational tides and radiation fields of a galactic nucleus. If the envelope of G2 was indeed forged by stellar winds, it opens up new ways of thinking about how stars survive near black holes. A dusty wind might serve as a form of camouflage, protecting the star from immediate detection, and even acting as a kind of buffer zone that absorbs and dissipates some of the energy from external gravitational forces. It may also create the illusion of vulnerability, causing observers to mistake a robust stellar object for a fragile cloud. But in reality, it is the wind-blown veil that gets distorted and torn, while the star remains unbroken at the core. This leads to broader implications. If G2's envelope is the product of a stellar wind, then there may be other stars in the central parsec of the Milky Way producing similar veils. The G-object family may not be rare curiosities, but rather part of a larger population of wind-shrouded stars. Each one would present a slightly different observational profile depending on the strength of its wind, the density of its envelope, and the angle at which we observe it. Some may appear as compact clouds, others as elongated filaments, and still others as nearly invisible wraiths orbiting the black hole. Furthermore, these wind envelopes could play a role in feeding Sagittarius A over longer timescales. While G2's material was not accreted in any significant way during its first pass, small fractions of gas stripped from these stars might slowly drift inward, joining the tenuous accretion flow around the black hole. Over thousands or millions of years, the cumulative effect of many such envelopes could provide the black hole with a low, steady diet, enough to sustain occasional flares, but not enough to trigger sustained, quasar-like activity. G2, therefore, may be more than a survivor, it may be a messenger, revealing how stars live and evolve in the galaxy's most hostile neighborhood. Its dusty wind, forged by internal pressure and sculpted by the pull of the void, stands as proof that even in the face of annihilation, stars can adapt, shield themselves, and endure. Before G2's close encounter with the black hole at the center of our galaxy, the prevailing belief among astrophysicists was that its fate had already been sealed. Based on everything we understood from computational models, painstakingly designed to simulate the dynamics of gas clouds near black holes, G2 was on a death march. These simulations, built on decades of theory about gravitational interactions, fluid dynamics, and tidal disruption, left little room for ambiguity. A diffuse gas cloud, without a core object to hold it together, approaching within just a few hundred astronomical units of a supermassive black hole, should be torn to shreds. Not only torn, but partially accreted. In essence, the virtual G2 was destined to vanish. Using computational fluid dynamics and relativistic gravity, researchers modeled how a cloud with G2's estimated mass, about 3 times that of Earth, and its dimensions, roughly 100 astronomical units across, would behave as it spiraled into the gravity well of Sagittarius A. In these simulations, the outer edges of the cloud would begin to elongate and trail behind long before the closest approach. The cloud would become a stretched filament, with significant portions of its material stripped off by tidal forces. Some of this material was predicted to plunge inward, potentially feeding the black hole and lighting up the surrounding region with a bright X-ray or infrared flare. The remainder would be scattered into more eccentric orbits or dissipated completely. What these simulations didn't expect was survival. They showed gas dispersing, not recoalescing. They showed a flare, not a fizzle. The model clouds that passed so close to the black hole didn't emerge on the other side. They were destroyed. Yet reality had other plans. As the real G2 made its much-anticipated approach to Sagittarius A in 2014, astronomers around the world gathered data from some of the most advanced telescopes available. Keck in Hawaii and the Very Large Telescope in Chile peered into the dust-choked center of the Milky Way using adaptive optics and infrared imaging. They waited for the signs, the brightening, the disruption, the evidence of chaos. But what they saw was, strangely muted. G2 was stretched, yes. Its shape elongated into a teardrop trailing a faint tail of material. But the core remained intact. It did not explode into ribbons. It did not vanish. And most baffling of all, Sagittarius A remained relatively silent. No massive flare erupted. No dramatic spike in X-ray or infrared emission appeared. The black hole barely noticed. This stark contrast between prediction and observation was both a disappointment and a revelation. It exposed the limits of our models, and the importance of assumptions that go into building them. Most of the early simulations had treated G2 as a pressure-supported, homogeneous gas cloud, a blob of ionized hydrogen without any internal gravity of its own. That's a reasonable approach if G2 was truly a free-floating clump of gas. But it turned out that this assumption might have been fundamentally flawed. Post-encounter analysis forced scientists to revise their models, to ask, what if G2 wasn't just gas? What if it had a gravitational center? A compact object, like a star or a stellar remnant, could act as a stabilizing core, maintaining the integrity of the cloud even as it experienced immense tidal forces. With a central object exerting its own gravity, the outer layers could be stripped, but the core would survive and continue shedding gas, perhaps even forming a new envelope over time. When new simulations were run under this assumption, the results aligned much better with the real observations. These revised models showed a tidal elongation, not destruction. They predicted the dimming and reformation of the envelope, not a catastrophic disruption. And they explained the absence of a major flare from Sagittarius A. The density and mass of the gas lost from the envelope simply weren't high enough to trigger noticeable feeding activity from the black hole. In a way, this comparison between simulation and reality was a wake-up call. It highlighted the importance of hidden variables, the things we can't see, like a star buried inside a cloud, and how much they influence outcomes in the universe. G2 showed that even our best simulations are only as good as our assumptions. When those assumptions miss the presence of a compact core, or misjudge the distribution of mass, the entire forecast can fall apart. But this discrepancy wasn't a failure of science. Quite the opposite, it was science at its best, an unexpected result pushing the boundaries of knowledge and forcing theories to evolve. Astronomers didn't discard their models in frustration. They adapted. They refined. They went back to the equations and introduced new variables, embedded stars, dust dynamics, outflows from stellar winds. And with each revision, the new simulations came closer to what nature had shown us in real time. Moreover, this event changed how we approach future predictions. No longer can we assume that clouds near black holes are simple. They might not be clouds at all. They might be something far more complex, stars in disguise, merger remnants, or entirely new classes of objects that don't fit neatly into our current taxonomies. Each new observation now comes with a healthy dose of humility. G2 taught us that the galaxy still holds surprises, and that we must be ready to adjust our models when reality deviates from expectation. In the years since G2's encounter, new computational efforts have continued to refine our understanding. Advanced magnetohydrodynamic simulations, taking into account magnetic fields, angular momentum, and feedback from stellar radiation, now show more nuanced outcomes. Some clouds might survive. Some might not. The line between survival and destruction is thinner, and more dependent on internal structure, than we ever imagined. G2's endurance didn't just rewrite one prediction. It set a precedent for how we interpret every future object that strays near a supermassive black hole. It reminded us that in the cosmic theater, simulations are valuable rehearsals, but reality always has the final act. Despite over a decade of observations and theorizing, G2 remains, at its core, an unsolved enigma. It defied predictions, reshaped our assumptions, and introduced new possibilities about stellar evolution and black hole behavior. Yet at the heart of its tale lies a swirling mass of unanswered questions. What exactly is G2? Where did it come from? What is it made of? And perhaps most intriguingly, what happens next? Let's start with the biggest unknown, G2's true nature. Is it a gas cloud, a young star, a post-merger object, or something even stranger? Each hypothesis has supporting evidence, but none of them can be confirmed with total certainty. If G2 is a young star, perhaps born in the galactic center or nearby and migrating inward, it would need to have formed in one of the most hostile environments in the Milky Way, raising questions about how such a delicate process as star formation can survive amid the gravitational chaos and high-energy radiation of the central parsec. Alternatively, if G2 is the aftermath of a stellar merger, perhaps two stars that spiraled together due to gravitational interactions or orbital decay, then where did this merger take place, and why did it happen so recently? Mergers are rare and violent events. If we caught G2 in the aftermath of such a collision, then we're witnessing a cosmic wound still glowing with the energy of its creation. But if that's true, how many other merger remnants might be hiding in the galactic core, unseen beneath veils of dust and ionized gas? There's also the possibility that G2 is not a star at all but something more exotic, a compact remnant like a brown dwarf, or a stellar black hole cloaked in ejected material. Could it be a binary system masquerading as one? A neutron star in disguise? The difficulty lies in the fact that G2 has never been resolved in enough detail to see what, if anything, resides at its center. All we have are the indirect signatures, its infrared brightness, its behavior under tidal stress, and the faint emissions that whisper of hydrogen and dust. Then there's the question of its origin. G2 appears to be bound to the galactic center in a highly elliptical orbit, one that takes it plunging close to Sagittarius A before flinging it far out again into the crowded regions of the inner bulge. But where did that orbit begin? Did G2 originate within the central parsec, perhaps ejected into its current path by gravitational interactions? Or was it born further out, maybe tens or hundreds of light years away, and slowly drawn inward over time? If G2 formed outside the galactic center, it may have migrated inward due to dynamical friction, losing energy as it passed through the thick forest of stars and dark matter populating the galaxy's bulge. Or it might have been thrown into a plunging orbit by a violent encounter with another star or even a small black hole. Tracing its past trajectory is nearly impossible with the current data, but future refinements in orbital tracking might help reverse engineer its path. The composition of G2 is another persistent mystery. Observations suggest it contains ionized hydrogen, likely heated either by stellar radiation or tidal friction. Dust is present too, which glows in the infrared when warmed. But what's the exact ratio of gas to dust? How much mass has it lost since its closest approach? And how much of what we see is actually newly ejected material versus remnants of an older envelope? Understanding its composition isn't just a matter of classification, it's also key to predicting G2's future. If the envelope continues to dissipate, will the central object, if it exists, eventually be revealed? Or will it shed more material and rebuild its cloak, continuing its masquerade for another orbital cycle? If the object is indeed a star, it might evolve over time, altering its wind strength, radiation profile, and visibility. If it's a merger remnant, it could stabilize or undergo further changes, perhaps even triggering new forms of mass loss. Another question is whether G2 will ever interact with the black hole in a more dramatic way. On its current orbit, it may return for another close pass in the far future, possibly thousands of years from now. But before then, its material might begin interacting with the black hole's accretion flow or even with other nearby G objects. small gravitational nudges could subtly change its trajectory. Alternatively, the envelope it sheds could contribute incrementally to the black hole's feeding, too little to spark a flare on its own, but part of a long-term trickle of mass that sustains Sagittarius A in its quiet mode. Then there's the lingering question of how unique G2 truly is. The discovery of other G objects, G1, G3, G4, G5, and G6, suggests that G2 may be part of a broader population. Are all of these objects stars surrounded by dust? Are they different evolutionary stages of the same phenomenon? Or are they each telling a different story? Some stars, some clouds, some mergers, some perhaps even rogue planets or failed stars? If G2 is just one of many, then solving its mystery could unlock a whole new class of astrophysical entities. The observational challenge remains formidable. Even the best telescopes struggle to resolve objects in the galactic center, where extreme crowding, interstellar dust, and intense radiation make every image an exercise in interpretation. But with the advent of next-generation instruments like the James Webb Space Telescope and the Extremely Large Telescope, we may soon obtain better infrared data, finer resolution, and deeper insight into the galactic core. Until then, G2 drifts on, silent, elusive, and enduring. It circles a black hole that should have torn it apart. It glows faintly in the dark heart of our galaxy. And it carries with it a list of unanswered questions as long as its luminous tail. Every orbit it completes, every observation we gather, draws us closer to the truth. But for now, G2 remains a riddle wrapped in dust, traveling through the shadow of a monster. G2's legacy is not simply written in the dust it left behind as it careened past the Milky Way's supermassive black hole. It's written in the rewiring of our cosmic understanding. In a universe where gas clouds were thought to be fragile, fleeting phenomena doomed to be devoured or dispersed near black holes, G2 broke the narrative. This single object, enigmatic and resilient, reshaped our grasp of how stars behave in the heart of galaxies, challenged our theories of accretion, and cast doubt on long-held assumptions about the boundaries between destruction and survival at the edge of gravity's most powerful well. Before G2, the gravitational influence of Sagittarius A was envisioned as a near-absolute force, merciless and unrelenting. Anything that dared wander too close, particularly something as ephemeral as a gas cloud, was thought to be shredded by tidal forces, its remains spiraling inward to be consumed in a flare of X-rays and infrared light. But G2 defied that scenario. It passed within 260 astronomical units, closer than Pluto is to the Sun, yet it emerged on the other side not only surviving but still largely intact. It didn't feed the beast. It didn't evaporate. It endured. That endurance sent shockwaves through the astrophysical community. Suddenly, we had to reevaluate our models of tidal disruption and accretion. We had to ask, what does it take for an object to survive such a close encounter? What does this say about the true feeding habits of Sagittarius A, and by extension, other supermassive black holes? Could it be that these monsters are more selective in what they consume? Could their quiet phases last longer because many objects, like G2, simply pass too quickly or contain too little mass to make a difference? This shifted the framework for understanding the so-called underfed black holes at the centers of many galaxies. The idea that everything that approaches must be swallowed was replaced with a more nuanced picture, one where black holes are not omnivorous vacuums but rather complex, inefficient engines that only accrete matter under very specific conditions. In this way, G2 helped humanize the monster at the Milky Way's heart. It made it less mythic, more comprehensible. G2 also had a dramatic impact on how we classify and interpret objects in the galactic center. What had once been considered a gas cloud was now being reconsidered as possibly a star, or a merger remnant, or an entirely new class of object, compact, dusty, and enduring. This opened the door to reinterpreting a wide array of other structures that had previously been dismissed or miscategorized. G2 proved that not all clouds are clouds. Some may be stars in disguise. Others may be hybrids, existing in a transitional state between a dense object and its ejected veil. This possibility inspired the systematic search for G2-like bodies, an endeavor that revealed the G-object family, G1, G3, G4, G5, and G6. Though not identical, these mysterious bodies shared enough features with G2 to suggest a broader pattern. A new class of objects had effectively been born, not by invention, but by revelation. And G2 was the prototype. The pathfinder. On the observational side, G2 also pushed our technological boundaries. Tracking its motion, morphology, and emissions over the course of several years demanded the best our instruments could offer. Facilities like the Keck Observatory and the Very Large Telescope had to operate at their limits, using infrared adaptive optics to peer through the thick smog of interstellar dust that shrouds the galactic core. In doing so, G2 became a kind of natural laboratory for testing our tools and techniques, validating our ability to study extremely faint, fast-moving objects near a black hole. The data gathered during its passage didn't just enhance our understanding of G2, it improved our understanding of the environment around Sagittarius A as a whole. It helped refine our maps of the black hole's accretion flow, the surrounding magnetic fields, and even the orbits of other nearby stars. These stars, some of which also travel on eccentric, plunging trajectories, could be the next G2s. And when they make their pass, we'll be ready. From a theoretical standpoint, G2 forced a reconsideration of how stellar evolution unfolds in extreme environments. Whether it is a young star wrapped in dust or the remnant of a merger, it represents an evolutionary path that we did not fully understand. It showed that the galactic center, once thought too hostile for star formation or survival, can in fact support a rich tapestry of stellar processes. Stars can be born there. They can die there. And in rare cases, like G2, they can persist in a form we barely recognize. There's also the philosophical legacy to consider. G2 reaffirms a fundamental principle of scientific discovery, that sometimes, the universe doesn't behave the way we expect. And when it doesn't, our responsibility is not to force the universe into our models, but to let our models adapt to the universe. G2 taught us humility. It reminded us that certainty in science is provisional, that every observation holds the potential to rewrite what we think we know. In classrooms, research papers, and observatory mission designs, G2 now serves as a case study in caution and curiosity. It's cited as a textbook example of how unexpected outcomes are not failures. They are opportunities. They are doors that open to new ideas, new investigations, and new paradigms. And so, G2's legacy stretches far beyond its orbit. It lives in the shifting theories of accretion, in the reclassified objects of the galactic core, in the new searches for dusty stars and merger remnants, in the understanding that even in the deepest shadows of the galaxy, there are stories not yet told. A cloud that was supposed to vanish didn't. And in that act of survival, it changed everything. In the center of our galaxy, buried beneath layers of dust, radiation, and swirling gravitational tides, lies a place few dare to tread, an abyss where time stretches and space itself warps. It is here, in this place of unimaginable forces, that a faint object once drifted silently into view. No one expected it to last. No one believed it would endure. But it did. G2, born of mystery and wrapped in veils of glowing dust, approached the one thing in the Milky Way that devours light, matter, and even the memory of motion itself. Sagittarius A, the monstrous black hole at the core of our galaxy, waited with patient stillness. Astronomers held their breath. Simulations whispered predictions of doom. And the cosmos, it seemed, had already made up its mind. But the universe had written a different story. As the cloud descended into the belly of the galactic beast, something unexpected happened, not destruction, but resilience. Instead of flaring into final brilliance, instead of unraveling like a cosmic ghost, G2 survived. It passed through the shadow of the void and emerged, dimmed, distorted, but unmistakably there. That act of survival echoed far beyond the black hole's invisible horizon. It stirred the foundations of astrophysics, sparked new theories, and made us question what we thought we knew about the interplay between matter and gravity, stars and gas, destruction and endurance. G2 wasn't just a cloud anymore. It had become a symbol. A scientific parable. Because in that silent arc through the most dangerous place in the galaxy, G2 became more than an object of study. It became a metaphor for the resilience hidden within the cosmos. It reminded us that even in the heart of darkness, not everything is destined to be consumed. That sometimes, fragility is an illusion. That what seems soft and insubstantial may conceal a hidden core of strength, invisible but unyielding. And so G2 continues its orbit. Quietly. Patiently. Still watched. Still studied. Perhaps still hiding secrets. It loops around the black hole not as a sacrifice, but as a survivor. A reminder that the cosmos, in all its power and peril, also holds room for endurance, for surprise, and for stories not yet finished. In the end, G2 approached the monster not as a victim, but as a whisper of cosmic defiance. In the heart of darkness, a fragile cloud orbited the edge of eternity, and lived to orbit another day. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.